Good morning, everybody. Welcome to the pre-meeting tutorial. And this morning's tutorial is on electromagnetic transient analysis simulation tools. And Julia Matevosyan, who's the chief engineer of ESIG, has organized and will be moderating the tutorial. We've got a great lineup of presenters for the tutorial, and I'm looking forward to learning a bit myself, and I'm hoping everybody else will learn a bit too about the wonderful world of electromagnetic transient analysis. So Julia, I'm sure she's a stranger to most of you. Most of you don't know her. She's not very widely recognized in the industry, but she's the chief engineer at ESIG. I'm just joking, of course. And I think she doesn't really need much of an introduction, but she's a real bundle of energy. She's staying on top of what's going on with IBRs all over the world. A lot of people have learned a lot from her. I know I have. And also you've seen the magazine in the back, the last issue of the IEEE P&E magazine, the March-April issue is on inverter-based resources. And Julia was the co-editor of that magazine. So I'd encourage you all to read that. And without any further ado, Julia, I'll turn it over to you.
All right. Thanks, Charlie. Good morning, everyone, and thanks for coming to our EMT tutorial. Let me go ahead and get started. Charlie already introduced me, so for those of you who don't know me, I'm Julia Matevosyan. I'm chief engineer at ESIG. At the tutorial today, we also have Matt Richwine, who is founding partner of Telos Energy, a consulting company, and then Lukas, Unruh, who is lead studies engineer in Electranix, also consulting company. Matt is based in the US and Lukas is based in Winnipeg, Canada. All right. So what we have today, I'll start with a short introduction to just introduce why are we talking about EMT here, what's the need. And then Matt and Lukas will dig deeper into identification of need for EMT studies, data intake and organization, system model construction and quality assurance. And then we'll have time for Q&A. For Q&A, you can just come here to the mic, introduce yourself and ask a question, and then we'll ask you to sit down after I ask a question so it doesn't turn into discussion, and so that other people have a chance to ask questions. And then we'll have a coffee break for half an hour, and this is where you can have a discussion, and then continue with talking about simulations, analysis, and actions and mitigations. And then at the end, we'll conclude with a software tool vendor panel where 4 different software vendors that work with EMT will present about their tools and talk about what are their tools best for to use and what are the capabilities, what are limitations. Hopefully they'll mention some limitations too. And we'll have a short Q&A. We'll run 15 minutes into lunch, so I hope you don't mind. And if you do, that's okay. And after that, we'll conclude and have lunch, and you can catch up with vendors for more Q&A during this 3 days of the workshop. All right, so introduction and why do we need EMT studies. So previously, EMT modeling and analysis was a kind of special type of studies and used for local phenomena like lighting evaluation, insolation coordination, and so on. With proliferation of inverter-based resources such as wind, solar storage, battery storage, fax devices. So these are power electronic based devices that you may have on transmission grid. HVDC converters and also power electronic interface loads lately. So the dynamic behavior of a power system is becoming impacted by fast response of these resources. And we are starting to see new stability phenomena on the grid, such as subsynchronous control interactions between different power electronic sources. So we need studies and simulation environment that is capable of capturing this fast subcycle dynamic phenomena. What was additionally discovered in more recent disturbance events where multiple inverter-based resources unexpectedly tripped after normally cleared fault events, is that models, more detailed models, can help capture some of this behavior during, interconnection process and during studies. But what's also important to mention is not only you need more detailed model, but also more accurate model, and it's not necessarily the same thing. I'm sure Lukas and Matt talked to length about that. So talking about disturbance events, what you see here in the bar chart is all different disturbance events that were reported and analyzed by NERC, starting from 2016, and the last one that was reported in Utah in 2023. So it's continuing to happen. In yellow, these are solar events, in blue is wind, and gray is showing synchronous generation that disconnected during same time. And so in these events, especially during last Texas events in Odessa, Texas in 2021 and 2022, it was discovered that 3 of the causes of inverter tripping were actually, you cannot even capture it in the phasor domain models because these are subcycle phenomena. They trip on instantaneous changes in variables on the grid. And to add a point to accuracy of models, when ERCOT went back and looked at EMT models, ERCOT actually collects EMT models for a while now, these phenomena were not modeled there. So they could not see same behavior as they saw in reality. They could not see it in the models. So not only having detailed model helps, but it still needs to be accurate. And if you have detailed model that doesn't reflect certain behaviors, it still doesn't help. So looking forward, if you look at interconnection queues around the US today, we have, so this is data from end of 2022. At that time, there was 2,000 gigawatt of generation in the interconnection queues across the US. If you look at makeup of these generators, 96% of them are inverter-based resources. So we have more and more of these resources connecting to the grid. EMT models are not important just at time when you need to do EMT studies, but as I mentioned, with example of previous NERC disturbance events, they may help to detect issues early during interconnection process, and you can also use them for benchmarking PSCAD models. So you have, 2 sets of models that you can benchmark against each other. And also when events start happening on the grid, you can play back an event into the model and you can validate both of these models based on event analysis. And so if you don't have these models, there is a missed opportunity to validate these models and make sure that what you studied is actually what's happening in the field. One other thing, even if you look at areas that are already collecting EMT models, you can see that sometimes they need to study an area where there is already older IBRs connected, and they're looking just at this new IBRs, but they cannot study it completely because they don't have models of old inverter-based resources. And now as they're going back, trying to get these legacy models, the generator ownership changed hands, so nobody actually knows what's in this plant anymore. Manufacturers gone out of business. Manufacturers are not supporting this product anymore. So it becomes very difficult to get accurate models of this equipment after the fact and, few years down the line. So basically all of this to say, by the time EMT study is needed, starting to think about collecting models is way too late. And so we need to think ahead. And so what I mean by this, if you look at the interconnection process today, this is kind of US based, I would say, the way interconnection process works here. By the time you start doing impact assessment studies, ideally, you already need EMT models. You need to collect these models. You need to quality test these models to make sure they initialize properly and they work. And also use it for benchmarking with phasor domain models. So that's kind of one step towards model validation. But then as you move across the interconnection process, maybe at this stage, at this early stage, manufacturers are not even sure what kind of equipment they're going to go for. So there is a really high chance that these models will change over time and they need to be updated. And yes, I hate to bring the bad news here, but there will need to be some reiteration as the models get changed and updated. Some of the tests and studies will need to be repeated during interconnection process, but it contributes to the overall accuracy of models, accuracy of studies, and eventually reliability of the system. And further on, as the plants become operational, even after commissioning, as the events are happening, it's a real first chance to validate these models. Because before that, you don't do, large disturbance on a real plant during commissioning, and you don't have a good chance to check your models for large disturbance performance until it actually happens in the field. So there is a lot going on in EMT modeling area these days. So some of the areas, like I mentioned, ERCOT, ISO New England, California ISO are collecting EMT models during interconnection process, and they have detailed requirements for model quality testing and model validation. In 2022, in April, IEEE 2800 standard was approved, and this is a standard for performance of IBRs connected at bulk transmission system level. And among other things, it has requirements for EMT model data requirements. NERC Mod 26 standard currently is undergoing revision, and there are in the draft requirements for EMT modeling are already included. Last year, NERC Inverter-Based Resource Performance Subcommittee, which is a stakeholder group that focuses on inverter-based resource performance, and these are inverter-based resources connected at bulk power transmission level, bulk power system level. They have released a reliability guideline on EMT modeling of IBRs. Fourth quarter 2023 also requires submission of accurate and representative EMT models at the interconnection request stage. I put in red because this requirement is only in case if the area is actually conducting EMT studies. But as I mentioned in my earlier slides, this is too late to collect EMT models if you need a study. So basically, I would encourage everyone, and if you work for system operator, transmission owner, to start thinking about EMT modeling way ahead and collecting models during interconnection process, regardless if you're doing EMT studies or not. And then there are ongoing projects at NERC that look at EMT modeling and affect a number of NERC standards, and these are currently in drafting. So EMT modeling basically coming into NERC standards, coming into FERC requirements, IEEE standards, and so this will be commonplace in a few years. So I mentioned reliability guideline from NERC. I have it on the left-hand side of the slide. It's linked up there. So once you get the slides, you can actually go and have a look. The first volume of the reliability guideline focuses on model requirements, model quality assessment, screening for EMT study needs, and then also for assessment of voltage write-through capability and performance during interconnection process. So basically, that's what I mentioned, is that by having EMT model and during quality testing of the EMT model, you can actually also check some of the conformance with interconnection requirements in the area as a part of this process. And then after the first volume of the reliability guideline was published, Inverter-Based Resource Performance Subcommittee decided to spin off a task force. So now there is NERC EMT task force. It's open to everybody who is interested to participate, and they meet monthly and talk about EMT modeling for transmission connected inverter-based resources. So you can see contact information there for Anton at NERC, who leads this group. And again, it's this open stakeholder group. Please join if you want to learn more about EMT. And they are currently wrapping up the volume 2 of reliability guideline, and this one is focused on EMT studies. So basically, past the time you collected models, now you need to do EMT studies. What do you do? And you have some items in the scope listed there. They are about done, so you will see this coming out in a couple of months. All right, so with that, and without any further ado, I'll pass it on to Matt.
Thanks, Julia. Try to get this hooked up. Okay. How's that? Can everyone hear me okay? Sounds good. Okay, great. Thanks. Good morning, everyone.
My name's Matt Richwine from Telos, as Julia mentioned, and yeah, really excited to be here to talk a little bit more about our experience with EMT modeling. And just to, I think Julia did a great job setting the stage in terms of what's going on broadly in the industry. Why are we talking about this? Why is this the right time to be talking about this? EMT has been around for decades, and why is it coming to the fore now? I think it's very clear what's been happening recently, what's driving us towards EMT. And that reason is there's a lot of EMT consultants that really need more business. And so we got a couple EMT consultants up here to tell you why you need EMT. And so get ready, right? Because you're going to need it all the time for everything. And that's how we like to roll. But that's really not it. And what we're going to cover here in a couple hours is, didn't anyone ever tell you, don't ask the barber if you need a haircut? But what we want to share here is an understanding. There's a lot of what we can't cover. There's a lot of topics that we are going to touch on that could be their own tutorial. And so what we want to share here is to identify when you need EMT, when you don't need EMT, and what goes into it, and to tie that into what folks are generally more familiar with, which is positive sequence, fundamental frequency, or transient simulation tools. So to hear again, why do we need it? For accuracy, for studies, for the reliability, so that we can make sure that when we have, when we're seeing these events that are occurring out there in our rich regions, we understand we can really have the ability to predict that. And the phasor domain tools are clearly have been falling short of that for certain types of events, for certain regions. And understanding the difference of where it really applies and where phasor domain tools, as we're talking about, they're not dead, they're not under attack. They're basically being augmented by EMT type studies. And that's one of the messages here that I think is important. And we would like to help draw the lines based on where we've seen it from our experience on where that is. Where do you draw the line? How do you know when your phasor domain tools are not going to give you what you want? And then if you do go into the EMT realm, what does that look like? Where are the potholes? What things should we be watching out for? And I thought this list also was great. I like the dominoes slide too of the NERC reports, right? But if we just pull the list from NERC and look at the time scale on that from now till 2003, you can see 2/3 of the major events have been in the last 6 or 7 years or so, right? So we're seeing the impact of the changes that are happening in the grid in a way that is not so desirable, and in a way that we have the ability to make some changes. So tying this into the modeling a little bit more, starting with level setting here, dynamic models, all models are wrong, some are useful. I think this is a great quote. I think it hits the nail on the head, and just understanding where we are in terms of there's a continuum of models out there and of model software tools. They're all wrong. And the question is, they're wrong in different ways, in different aspects. And they're also, of course, I say this in tongue in cheek, but they're also very right in a lot of ways. But understanding which ways the ways in which they're limited and the ways that they do have the high fidelity is really important for when you conduct a study and then need to go and draw conclusions from that study. And there's, of course, the trade-off with this, where you have simpler models that make more simplifications and are, in a sense, less accurate, but they're easier to use, they run much faster, and there's value in that. And then there's the other end of that spectrum, the highly accurate models. They have a lot of data inputs, a lot of computation involved, and they're a lot more difficult to use. And there's value in that too. And they both have trade-offs. And it's just understanding where, depending on what your challenge is, what risk you're trying to identify, where do you really want to be on this continuum? Sometimes you want to be on the left side and sometimes you want to be on the right. And understanding where you are on this continuum and what the limitations are of those models is really important, and knowing what level of confidence you should have and kind of where to go when you need more confidence. So again, talking more generally and trying to tie it to what's more familiar, the positive sequence tool set versus the EMT tool set. So in the positive sequence world, these are a little bit more towards that left end of the spectrum. There's more simplifications. There's a looser model product relationship generally. The time seconds are in the milliseconds, or excuse me, the time steps are in the milliseconds level. They're only looking at positive sequence, fundamental frequency, or very close to it. And there's many simplifications that are intentionally made about the equipment to get it to work in that environment. And when done correctly, they are very useful and will continue to be so. There's also some aspects of the tool that they're not as well equipped to handle. For instance, when we talk about transport delays or other delays, for instance, that show up in communications between or within a plant. So for instance, in inverter-based resource plants, between a power plant controller and the inverters, there are signal passing. There's signals that are passed that have transport delays in the groups, and that can really matter. And those are not as well represented in positive sequence tools. There's also positive sequence tools tend to be, again, a little bit simpler to use, fewer software dependencies. And contrast with EMT, where there's the much tighter model product relationship, the time steps are much finer. We have full three-phase representation using the differential equations. It's very highly detailed. The transport delays and some of these aspects that introduce nonlinearities into the simulations, into the control loops, can be modeled accurately. And there's a price to pay for that. It's more complex software. There's more software dependency, so there's more software aspects of the tools. And then beyond that, there's a lot more input data and the models being very complex. So again, now that was a little bit more on the tools and the tool architecture. On the software models themselves, again, so this is now what goes into those tools. There's many equipment details that are, again, simplified intentionally. Because of the time step limitations and the design of the tools in the positive sequence models, the faster control loops are either omitted entirely or highly simplified. And the complex controllers, the limiters, there's, again, simplified. You don't have the representation of the power circuit. The DC side representation is basically non-existent. And the transport delays boil down to kind of simple first order lags and things like that. This isn't an indictment of the positive sequence tools. Again, these are the compromises that we've had to make, and it's just important to lay them out and understand what they are. In contrast, the EMT models are kind of, basically the opposite of all of those things. It is highly detailed, or can be, based on the product firmware. We'll talk a little bit more about that. This is kind of the capabilities slide, and then we'll talk about what really goes in. The faster control loops should be included in more detail. The complexity captured, the power electronic bridges represented, switching can be represented or may not be intentionally. DC side protections. This is also something that's kind of coming up more, to the extent that the DC side of that impacts the product's performance. That should be in there. And again, some of the details on the transport delays are can be accurately represented. So it's a much more capable tool set. Now, how do you develop the models that go into it? That is its own, really its own role for the folks that do this. The positive sequence models, again, because of the simplifications that are made, are often developed manually based on the product firmware that's designed, that's running. And so you'll have generally a human translation of that. The parameters typically also require translation. So when we're talking about these models, I'm thinking about it in terms of there's a control structure, an architecture that's generally fixed, and then there's a parameter set that goes into that control. And both of those together are equally and critically important to getting an accurate model. You can have a great control structure that is machine translated, like kind of one-to-one with the product. But if the parameters do not align with what's running in the product, in the field on the product, then it's not accurate. And so just remember there's a structure part and there's a parameters part, and they both need to be correct. So when we get into the EMT models now, there's there's generally two different approaches. There's a real code approach, which is a machine translation from the product firmware, which is often written in a language like C, to model code, right, which is generally underpinned in other things like Fortran or what have you. And so the programming languages are not identical, but they can be mapped and done by machine translation. But there's some notes on this, right? Because that sounds great that we're kind of taking the risk of, or the possibility of human error out of that process. And that's not correct. There's still a manual aspect of it. There's still a human aspect of it. There's a lot of product firmware that is absolutely important to running a product, but it does not make any sense to run in a desktop simulation environment. So even if with a real code approach, a manual translation, or excuse me, a machine translation approach to developing the best model you possibly can, there's a lot of engineering judgment that is still required, as my kind of red stamp goes. But that said, if you can do that, if you can strip it out, there are advantages to doing it. It's becoming basically a best practice in industry. And oftentimes you can have the parameter set having a one-to-one correspondence between what's in the product and then what's in the model. We can talk a lot more about that later, but there's some good things about that. The other approach that's more kind of historically and conventionally been used is a manual translation approach, which parallels to the positive sequence model development, where you have an engineering team that is looking at the code that's running on the products and then basically rewriting that in the format that is digestible by the EMT tools. And again, it can both be done well. There's a kind of an organizational preference for how to do that. And so I think it's useful to be aware because there are some differences there. The parameters may need to be mapped, maybe not as directly. And there's also some industry working groups that are focused around particularly the real code models. Okay, so zooming in one more layer to the types of power plant models. And again, just to lay out the whole picture of positive sequence models, we have generic positive sequence models. This is the second generation generic renewable energy models, originally developed by WEC, often called the WEC models. And then we have OEM specific positive sequence models. In the generic models, I think it's something, those are widely used across the industry. It's a fixed product structure with a few switches to enable some kind of, to enable some differences in the control structure. And they're suitable for, and it's all open. And they're suitable for large system studies. There's a lot of advantages, I would say, to the generic positive sequence models. There are also some disadvantages too. When we look at the OEM specific positive sequence models, these are not white box, these are black box. They're developed by the manufacturers, and the model structure is what the manufacturer decides to make it, and can therefore more closely reflect what is being done in the actual controls. For that, there are some advantages. There can be some more fidelity in that approach. There are also some more complex software dependencies that come along with that. If there are any bugs or issues along the lines along those lines, you ultimately have to go back to the manufacturer because they're the only ones that have the visibility and can make those changes in most cases. That parallels what's been done with the OEM specific EMT models. They're proprietary, they're created by the OEM. It's black box from the manufacturers, basically exclusively. And they, again, have that increasing level of detail and complexity. And there's some extra hoops that go along with that. So, now when we get into EMT models, there are generic models that are being generated, as well as the OEM specific models, kind of like what was done for the positive sequence tools. For OEM specific models, they represent specific products and product firmware revisions. And so I intentionally use the word firmware here because we're not just talking about a make or a model of an inverter. The firmware continues to be up, is a good thing. These products are getting better and more capable, but you have to make sure that you're mapping to the firmware because you could have you could have two different makes of inverters. They look the same, the cap the same, but the performance is software defined and can be very different. And so we want to tie that to not only the make and the model, but the firmware release. Revision control cannot be overstated. Revision control cannot be overstated. I think this is some of the rigor that we're seeing and really trying to drive to show that, if we're at this level of fidelity, I mean, you really got to be there and be able to run it to ground and know what's on your machine and what's on your desktop simulation and make sure that those are aligned. Because we've seen too many instances, as Julia pointed out, where we thought we had it and we didn't. And we can't field test faults, or we're unwilling to do that for good reason. And so those differences don't show up until you have a real grid event. And so getting this right up front and having that rigor, and it's not the fun engineering stuff. It's not always, pretty. It's not what we really get excited about doing, but it's so critically important, especially broadly to continue to have the confidence of the industry and to be able to push these changes and these new technologies forward. The parameter set, so same thing, must be aligned. You can have the best control structure, the best model that comes off the shelf from the manufacturer, developed with all of the best practices, but if those parameters are not aligned, all bets are off. If you can do all of these, if you can follow all of these best practices, apply the rigor, we can have extremely high confidence in the models and what we're doing. And we've been able to do that with these field events where things went sideways, and then we go back and do it and replicate those. And the models can replicate the field events. And we've demonstrated that. And that's a huge win, that part of it. Everything else leading up to that is the room for improvement. On OEM-specific models, a few non-engineering aspects, and I won't get on my soapbox here and now. They're proprietary code models, they're black box. There's almost always coming under an NDA because they are seen as basically the crown jewels of the manufacturers. They're technical differentiators, and all of their IP failed into this. And so they want to protect that. And that's fine. And that's important. But when you have now the legal teams getting involved here, and the engineering teams are trying to get it done, and the legal teams are trying to control risk, and they don't quite understand what each other is doing, sometimes that gets hung up, and there's a process aspect, and it can get log jammed. And so what I would just say, my brief soapbox is, for the folks that are doing this, we've got to have a streamlined process on the legal aspects. Cover the legal aspects, protect what the organization's intellectual property, but have a streamlined process. Because if you have a request for a model and it takes legal team 4 weeks to get the NDAs in place just to have access to the model, that is going to become extremely painful as we really start doing this in more volume. Today, the industry maybe has kind of gotten away with that and said, okay, yes, get this process started because it takes a long time, but that's going to become increasingly painful. So there are some non-engineering aspects that have real implications on getting the work done and the timelines associated with all of this stuff. And I guess maybe I'm sensitive to that because after the legal team gets done with all of theirs, that just usually shortens the engineer's time frame to get the study done anyway. So I want to press the legal teams up front so the engineers have more time to do it and get it right. Generic models for EMT. I think initially this sounded like an oxymoron, maybe to me personally, but it's really not. Generic models have a value. And you just have to know where they fit, what role they play. So generic models are not tied to any particular manufacturer, model, or firmware. There's much greater uncertainty and fidelity. They, however, have a place for research, for academic studies, for training purposes. I think there's a tremendous amount of value there. And then there are also some other places where really there aren't any better options. And is it better to have a generic model than no model at all? That's a decision that's made on a case-by-case basis. And sometimes the answer may be yes. In kind of larger system level studies where you may not be as sensitive to the behavior of one particular model or group of models. And for instance, you have a legacy product. You have something or a project that's been out there for 15 or 20 years. There's basically no practical chance in getting an accurate model of that in some cases in any relevant period of time. Also for DER, where there are pockets of DER that are where there's enough to make an impact. Having some representation of the DER in aggregate, the best way to do that may be a generic model. Protection relays. I'm just going to curtail that point. Maybe Lukas could, if he wants to dive into that a little bit more. Great. So EMT models. So we're going to talk a little bit more about the types of studies that they're used for. Classical, fast transient studies, special studies, dynamic performance studies, research and academia. And we'll get into each of these in a little bit more detail over the course of the next few slides. So classical transient studies, so the original motivator for EMT, where you have studies like lightning, switching, fast transients, transient recovery, temporary overvoltage, energization types of studies, insulation coordination and design. These are very fast events that utilize extremely small, even kind of by the EMT standards, very small time steps to capture these phenomena. So very high bandwidth, and there's also, they're intended for a particular application like these insulating coordinations. The runs are usually very short periods of time. And your IBR models are simplified or neglected because they're just not playing a relevant role in these extremely short time periods. And the extent of the model is also very limited. So extremely high detail to the point of modeling the geometry of buswork and distributed parameter lines, and everything looks like a waveguide. And the dimensions and the spatial aspects become very important, and you have to put in a lot of detail. Your times are very small, but you can't do that, and is really not needed to do that at kind of a large system level. So I think it's important. This is generally not what we're talking about. So why do we have a slide on this? It's part in just kind of, again, level setting for the folks that are kind of historically exposed to EMT. This may be their impression of what those tools are for and do. And we want to differentiate that a little bit more. They have more uses. So special studies, protection studies, control design, so tuning, dealing with complex control algorithms, Harmonic analysis, again, it's one of the tools among many that can be used for those types of analyses. And real-time simulation, so testing the hardware in a partial simulation environment, or and so these are driven by a specific need, a specific risk that you're looking to address. And these are very common. One of the big ones that I think is more the focus of what we're talking about here, and especially with some of the events that have happened and the motivation that Julia was describing initially, is the dynamic performance need and assessing the risk and the behavior and the performance of these resources and altogether on the system. And so there's a new focus driven here by the energy transition, by the higher penetrations of IBR. So we have now control interactions. And briefly, what we mean here broadly is an IBR interacting with something else. Can be another IBR, could be a series compensated transmission line. And so actually just in those two, right, the field is wide open. That's a very broad topic. Subsynchronous oscillations. Again, these are some of the topics where we mentioned this. That could easily be a whole tutorial, or in fact a week. There's a number of different flavors of subsynchronous oscillations, from kind of SSR, where where this kind of the classic SSO, where you have synchronous machinery interacting with series compensated systems, to now SSTI, where you have inverter-based resources interacting with synchronous machinery, to subsynchronous control interaction, or SSCI, where you'd have inverter-based resources interacting with series compensated lines. And so there's a number of different flavors in that one bullet. That's its own little onion with its layers. Weak grid performance evaluation. So it's increasingly in many places now where you have either systems, or more commonly pockets of a system, that have very high levels of inverter-based resources and can have relatively low or non-existing synchronous machinery in the region. And that has its own dynamics and risks and challenges that are broadly captured under the weak grid banner. Fault ride-through evaluation. Similarly, if your performance in any of these is compromised, one of the ways it can show up is in the failure to ride through our planning disturbances. Performance capability verification according to the standard. This is increasingly, and NERC has been very active here. There's many standards that are under revision to tackle this, and making sure that the capability is what we think it is and what the simulation models are showing. And then event replication analysis. Again, this is, I think, a growing piece of it as we are collecting more high quality data from these events, so that when an event happens, we can really understand and get to the root causes more quickly and check them in the model. That's another aspect that's driving the use of these tools. So what kind of model is used? It changes. It varies depending on which of these categories you're interested in investigating. Big your model has to be, what do you include, what do you not include. These are a lot of the things that Lukas is going to get into in the next couple sections. Okay, so to do or to not do an EMT study. This deserves a careful consideration, because what we're describing here is really a step change in effort and computation and skills and things that the industry has historically done. And so getting that right for the risk or the study or the challenge that's in front of you really matters, because it requires a fair amount of investment on the part of whoever is doing it. And so that answer can depend on human resources, just the practical aspect of who's going to do this in the organization. And do we have the people and the experience? And do we have the tools that are there to enable them to do the best job and an efficient job of it? The complexity of the system, the technical difficulty associated with the analysis. There are some parts where I would say you could dip your toe into EMT and get some experience and scope that out. There are other challenges and risks that you're going to want to understand and study that require kind of a full deep dive into the cold water and understanding what you're facing and basically how much is there behind it is really important to know and to try to understand upfront. Other practical aspects, the availability of the models. So I realize I've been neglecting this entire half of the room. I'm sorry. So do you have the models available? If you don't have the models, and it's just not a given, it depends on the age of the projects that are out there, that legacy problem, which we'll hear plenty about, I'm sure, this week. But if you don't have the models, then you really are starting off kind of, with shooting there's only so much there's only so much confidence you can have, and in any conclusions that you would draw from a study if you don't have confidence in the underlying models that you're using. So if you have the good models that generally from the last few years, you can then start with saying, okay, we can get to a level of high confidence. But if you don't have the models, that's going to undermine your confidence at basically step one. And so do you even bother drawing a study or going through all of the investment of doing a study that you're not going to want to wager much or stake much on anyway? And then the impact of the consequences. What's the worst that could happen? How big of an event is this? How much risk can we tolerate? So, for instance, IBR ride-through impact. How many can you use before you are really worried? And even the kind of the phrasing of this question is like, wait, what? Lose? We don't want to lose any, right? And it's true, we don't, but there is the practical reality that we're facing is there is still some uncertainty. There's a lot of events the industry I consider is just collectively learning. We haven't seen the last grid event, okay? But the thing we have in our control is what can we manage the risk of the next one? And as we transition to getting better and better at this, let's make sure that we understand, okay, some of these trade-offs that we have to make, that we understand the exposure and the risk that's implied by those decisions. Historical observations, oscillations, events. So do you have some known issues, some lurking things out there that maybe you really haven't been able to nail down? And is this a method to do it? Can you see what's really happening? Can you gain insight from some of this higher fidelity that these tools can enable? If your system is going to change dramatically, and I guess, that's getting pretty common now, and it's kind of, okay, what's your definition of dramatic and how far out in the future? Network changes, new units coming online, we talk about, major installations, an HVDC terminal, for instance, new transmission. Also, the flip side of that coin, major retirements. Okay, are you going to have, a synchronous machine that has been on and run flat out for the past 3 or 4 decades, being maybe not even retired, but just economically decommitted for more periods of time in the past? And, decommitment and retirement from a 30-second simulation snapshot, it doesn't matter. If it's not there, it's not there. And so even if it's not a full-blown retirement, are your operations changing in significant ways in which you haven't had that experience in the past? Series compensation, very large interconnections, very large IBR penetrations. And mind you, I think one of the more dramatic examples here is, when we talk about very large IBR, yes, it's, a 1 gigawatt IBR project kind of catches everyone's attention. What flies under the radar for a little while is, 5 megawatt DER projects that creep into that feeder and over there. And then before you know it, you've got a couple gigawatts of DER that just kind of rose up and kind of snuck up on you. And so, these events that we've seen are kind of raising that to a higher consciousness. So when not to do an EMT study? If the risks, the concerns, the challenges can be evaluated in a simpler method or in a simpler tool, by all means do that. Even, I think, start there, right? This is the classic low-hanging fruit kind of thing. Do the simplest things, do the easiest things first, and step into it to make sure that you really need kind of the big hammer. You don't always want to run to, it's not the first tool you grab in the toolbox necessarily. If you don't have the resources, the people, the tools to do it efficiently, that can be a painful exercise in futility. Because of the demands that are placed on it, you can sink a lot of real resources, and everybody knows, is, I'd say, very aware of the opportunity costs of how people are applied. The labor market is very tight for this broadly, and particularly for this type of work. And so you want to make sure that if you're going to invest, if you're going to go in and do it, that you can do it well. An improperly scoped study, and there's all kinds of ways that this can manifest, right? And Lukas will get into, how do you scope it? What is the size, the extent? How many grid operating conditions should you look at? Do you need to look at? What is the cost of looking at more? The availability of models, again, we spoke about that. And if the results wouldn't impact decision-making, or it's kind of within your tolerance for risk, then, maybe there's another way to do it. And that deserves a lot of consideration. But one of the key things here is the answer may be no, or maybe not at this time, or not for this study, or not for this concern. We don't always need EMT. In some sense, it's a method of last resort, but it's just that last resort is coming more and more. But when we do need it, we have to have the tools, we have to have the experience, the models, and the expertise ready. And that takes time. And so for the folks that may be looking at this and saying, okay, I'm not checking all of these boxes that Matt's talking about, our processes, our tools, and what we're doing, they're right for what we have right now. But that's not enough. Because of the time it takes to spin up and develop this core competency in EMT, you have to be looking ahead. You cannot turn on an EMT team or a tool set or a study in a day, a week, a month, really even a year. It's a multi-year process to get that, to develop that capability, even when it goes well. And so getting ready and anticipating the need and starting to dip your toe in, basically, and gain that experience and find trusted partners and find ways to do it will help you prepare such that when you get to that point where you say, oh boy, like we had this event, we didn't anticipate it, we have this new interconnection, or this project shifted from AC connected to DC connected, what are we going to do? That you're not starting from scratch. And so EMT, it supplements our existing tool processes. Again, I hope I tried to set the stage here a little bit more for the next work, that this is not something this is not all the time, everywhere, and it's not replacing the tools that have been so effective so far. It's the next tool in the toolbox that helps us answer the questions that the other tools can't when that is needed. So on that, I'm very happy to, I think we'll pause for a little Q&A, or?
We have Q&A before the coffee break.
Okay, so, and maybe I'll take a temperature. Are there any burning questions right now, or should we get on this boat here with Lukas? All right.
So, testing. All right. All right. Lukas here. Happy to be your captain today. All right. Thank you so much, Matt and Julia, for setting the stage. You guys did a great job. Yeah, I'm gonna take everyone through, I guess, a few of the more specific details of what are the processes involved in collecting an EMT model, what are the processes involved in gaining confidence in that model, and then later on we'll talk more about how to use that model in a study, how to build your study model using that detailed IBR model. So this first section here, we've called it EMT model intake. This goes by a lot of different names. You might call it model acceptance testing, or you might call like a verification procedure or something like that as well. And the main idea of this section is, essentially we talked a few times already. We want to be collecting EMT models before we essentially have a need to actually use those in a study, because for one, you just want to, basically as soon as you get a model, you want to start gaining confidence in that model by testing it, by probing it, essentially. And also, you don't know exactly when you're going to need that model in the future. So it's always good to, have that model and be ready for using it in a study when you need to, right? So you need to be prepared for that situation. So of course we need EMT models to do EMT studies, and we, they're essentially the fundamental building block of a larger kind of system level EMT study. So, we need to make sure that these models that we're using as kind of our fundamental building block are of high quality. And, if we don't do this, then we run a real risk of basically having useless studies. If we don't have good quality, inputs to our studies, then we're not going to have good quality outputs, garbage in, garbage out sort of thing, right? So yeah, and then another reason for doing this kind of like early on in the process, in terms of get an interconnection request, submit a model and start testing it, is that if you leave this down the road for when you actually need to use the model in a study before you test it, 90% of the time you'll find out that there's an issue with the model, whether it's just not behaving properly in terms of its performance, or whether it's just like incompatible with your system model. So we really need to take care of this as early as possible in the process, as we can. And I like this analogy that Matt actually suggested. Testing the model is a lot like buying insurance for a situation down the road when you might need that model. And if you don't do it, it's actually quite risky, because it's very hard to obtain a model for a legacy project, or one that is very far down the queue, compared to at the onset of the interconnection process, essentially. So collecting the model and performing model intake testing has a few sort of fundamental components to it. The first one would be essentially model requirements. So this usually takes the form of something like a checklist, where you're basically doing, you're verifying certain aspects, certain quality of the models, I guess you could say. You'd be looking at it for accuracy, right? And we already talked about this. Accuracy has two very important parts. You could say it's detailed, right? Detailed doesn't lead to accuracy in and of itself if those details aren't correct, essentially, right? You can build a very detailed but generic model, and it's not correctly representing any sort of specific OEM necessarily. So there's a difference there. And we have, within that accuracy, we have certain very specific accuracy features that we look for, kind of like as it pertains to the study that we're doing, right? So if we need to look for something, some very high frequency sort of phenomena, and maybe we want to make sure that the model switching is included, then we would require a switching model, versus other cases we can have a different type of model that is essentially more approximate at those higher frequencies. And then taking accuracy to the next level, right? Is the model validated? So this is something that's done in a few regions. In ERCOT, for example, they ask for sort of a unit level model validation report. So this is essentially checking the model against the performance of the actual equipment, or in one way or another. So typically, this is like a hardware in the loop type test, where you can kind of validate those controls against actual equipment. And that's kind of like, you know, awesome if you can get that for accuracy. And we don't always get that, right? But it's really great to have. The next big kind of aspect of modeling requirements is what we call usability, or some folks might refer to it as robustness as well. And this is essentially checking whether you're going to be able to use that model in your system, in a system model, in kind of an efficient way. Okay, so if you get a model and it requires like a very small time step or something like that, then when you're going to put that model in your big system study, it's going to really slow down, you know, the whole study to the point where it's not really feasible to work with that model in the study anymore. And then there's other sort of compatibility aspects of the model that we would include in that usability space as well. The third big point there is whether it's site specific. And here, what we mean by site specific really does change as the project matures. So at the kind of like initial model submission stage, usually there is nothing built yet, right? Depending on when you're collecting models, there may or may not be something built. So that site-specific thing will mostly be referring to, you know, does it correlate with the rest of the data that's been submitted, right? Does the information match what's in their application, for example? Does it match what they submitted for their phasor domain model, et cetera? But as the project matures, that sort of rigorousness will change from looking at, you know, what they wanted to build to what they actually did build, right? In terms of what we're thinking of in terms of site-specific. And of course, we want documentation whenever possible of documentation for how to use the EMT model. And that could be, you know, the inverter level model. It could be the plant controller model, and it could be the whole site. We can have documentation kind of targeting those different aspects of the plant. One really big part that's kind of gaining momentum, I think, in industry of this process is performance testing. And what we're looking for here, or historically, what we've looked at here is whether the plant is likely to perform with sort of basic performance needs of the system. And you know, we would test things like simple ride-through tests, making sure it can kind of operate in a reasonably weak system, and make sure it can do voltage support and frequency support and things like that. This segment has really been expanding, and in some places is really blown up. If you look at what the folks in Australia are requiring in terms of their dynamic performance accepting testing, it's like hundreds of tests. So it's very, very rigorous, and it takes a very long time. Yeah, and in this process may also include some benchmarking between EMT and RMS models, if that's kind of required based on the specific location. It's not something that everyone is requiring, and there's kind of, you know, there's some pitfalls involved in that process, which, you know, is a whole day we could talk about that, but we'll kind of leave it at that for now. But one thing, just going back to the performance testing, yeah, like we can make the performance testing as rigorous as we want during the kind of model acceptance process, but this performance testing is not a system impact study. And so there's always going to be, you know, limits in terms of what we can infer about the performance of that model in the context of a system. So it's never going to be the final arbiter of whether the model is going to pass any sort of dynamic performance assessment within context of a system. We're always using very simplified network representations in this phase. So that's just something to keep in mind. So here's just a very high-level example of what an EMT model might look like. So essentially, this is from a PSCAD solar farm example, which you can find from the website if you're interested. So the components here are an inverter model, a plant model, and then some plant impedances. Within that inverter model, within that kind of block that you're seeing there, there is the actual inverter itself, the DC to AC inverter. We have some DC side representation and a PV array in there as well. And within our model requirements, we have specific requirements targeting specific aspects of the plant, okay? Verifying and sort of exercising various aspects of the plant. So for the power plant controller, we would have, for the plant controller, the biggest thing you want to get right is the response time. And if there's any sort of like delays that are, that are in the real system in terms of passing signals from the plant controller to the inverter and things like that. These are the kind of transport delays that Matt was talking about. They're very important to capture at that power plant controller level. And then we'll have like a whole nother set of requirements kind of like for the inverter level. And then, if you want to see specific things modeled on the DC side, that'll be a whole nother, if you could have more kind of requirements for that part of the model. A few more notes on the model performance testing. This can look a lot of different ways depending on what kind of system you're in and what kind of market you're in and what's being required. So typically this is basically just a model and with a sort of voltage source that's behind an impedance. That's sort of the fundamental sort of single machine infinite bus representation that we will typically use to test models in. And this is of course very, very simple. There's not, like anything frequency dependent in the network equivalent or anything like that. It's typically just like a series RL sort of representation. And within that model, we can actually test a lot of things within that model. We can test fault ride through, voltage and frequency support, performance in a number of different ways. We can do voltage and frequency play-in tests. So we can take that source and we can start playing around with the voltage and frequency and the phase of that source as well. There's other test systems that have been proposed, like in the ISO New England region, for example. They kind of require a small portion of the system to be kind of included with the model as part of the model acceptance testing. So maybe like 2 or 3 buses from the point of interconnection, and that kind of enables you to apply like a line out, a fault and a line outage to see the kind of recovery with that sort of dynamic. So this can look a number of different ways, and I think probably we will see more alignment. I'm hoping we'll see more alignment in terms of what folks are asking for in these sort of test systems as things like IEEE 2800.2 comes online, which is going to essentially lay out exactly how folks should be testing plants against the IEEE 2800 performance requirements, which is something that is essentially missing in industry at this point. So one more note on this section. It's really helpful if organizations are able to publicly make their test systems and their testing requirements available, like on their website or something. And then folks can just go, an interconnection customer can just go and download that test system, and kind of before they even will submit their model, they can already get a head start and go ahead and start testing against requirements before they even submit their model. This really saves everyone a lot of time down the road for the transmission owner or whoever is going to be eventually collecting model. They can now require a testing report to come in with that model that states, hey, we already have compliance with all your modeling requirements and your performance tests. And so the TO really just has to do some fairly light verification on the performance that they're seeing in that sort of test report. And I think it's also really helpful for the developer because they can kind of like do that iteration in shop. Their consultant can do that iteration in shop. They don't have to keep passing it back and forth to the kind of testing entity. So. Yeah. So within this performance testing space, there are specific things that we will look for. And mentioned some of these already. So things like fault ride-through and recovery, we can keep a close eye on that. We can do, of course, balanced and unbalanced faults of varying durations. And another thing we can do is voltage and frequency ride-through by playing in a certain curve, like your PRC24 curve, for example. You could take those curves and play them into the model and get a feel for whether the model is going to ride through and perform acceptably for that sort of voltage or frequency profile. And we can kind of take that to the next level and do phase jump testing and even rate of change of frequency testing as well in our simplified system. And another thing that we often do, is do sort of a very preliminary investigation into weak system performance. So if you imagine our single machine infinite bus system, where we have a voltage source and an impedance, we can basically take that impedance and start turning it up, until things go wrong, right? We know eventually there's going to be a point where the plant is going to stop operating, and it's actually quite informative for us to have an idea of when that operating limit is in the model. Of course, this is one of those areas where, yeah, you can't, the system, the performance in the actual system might be way better and it might be way worse than what you're seeing in a test like this, because the network equivalent that you're using for this test is super simple. It's just like a series R and L, right? So this example here, you can see this plant went unstable here when we changed our short circuit ratio, which is a metric of system strength. When we change it from 3 to 2.5, we start to see some oscillations, and we kept turning down the system strength, and eventually it trips. So this is kind of in line with what we see for a lot of projects. They might go unstable a little bit higher or a little bit lower, but this is kind of general performance that we do see. And then another thing that we can do at this sort of model intake performance testing phase is if there's specific capability that we are looking for from the devices, it's very useful to test for that capability at this phase. So if you're looking for capabilities such as grid forming inside of your battery inverters or whatever, then this would be the phase at which you test that capability. So if you have, there's a number of folks out there who have gone through the process of creating grid forming specifications, and those specifications are constructed in a way that you can do that verification during the model intake procedure. So that's a great time for doing that sort of testing. And one other benefit to one argument for making the performance testing during model intake very rigorous is that this test system is going to run extremely quickly, and it's very easy to work with relative to what the interconnection study looks like. Okay, so you can test, the Australians are taking this to the next level, right? They're doing hundreds of tests in these simplified test systems. You can test, full, across the full reactive power capability range. You can test across the full kind of active power range of the device. You can test all kinds of different system strength and different kind of voltage and frequency profiles. So it's a very kind of sandbox environment for you to play with the model and probe it and to make sure that it meets your needs. Because inevitably in the system study, you're not going to necessarily be able to run everything that you would like to, right? You're not going to be able to run that model at full capacitive and full inductive power factors, for example. well, you could, but it would take forever, right? So there's more flexibility with that model in this sort of performance testing phase than you're going to be able to get at the kind of interconnection study phase. Okay, so this slide is pretty similar to one that Julia had shown before, but I'm going to focus on a couple aspects of the plant model that maybe changes from the initial interconnection application to kind of the kind of post-commissioning phase of the model, and what kind of parts of maybe the plant design we can focus on at various points along the way. So for the initial interconnection, we want to see the full plant model. We want to see a reasonable plant design, and we should note that at this point, some aspects of the design are going to be generic, and it's probably okay for that to be generic. So for a plant controller, for example, that's typically one of the last things, at least in my experience, typically one of the last things that gets decided. And so we often see generic plant controllers at the kind of interconnection application phase, and that's usually okay. Maybe DCSAD representation, maybe they don't have some of those details worked out yet, exactly which solar panels they're going to use or whatever, or what that looks like. So that, there's some aspects of the design that can initially be somewhat simplified. But we want to see a plant that gives a reasonable response to a generic grid equivalent, something that we can check the quality and initialization of very well. And we essentially want to have a model that's going to be useful for preliminary interconnection study or design evaluation. And you can see the figures in the top here. This is kind of the plant construction phase, right? So all the pieces are kind of slowly coming together, and this is kind of the first shot at it. Now, somewhere along the line, you're going to have the final design will be determined, and that could be before construction starts. It could be during construction. It could be near the end of construction before the final design is determined, right? So the kind of construction phase is not really relevant necessarily to this sort of timeline. But at somewhere along, you should be having a final design basically determined. So at this point, we should have exact plant design and equipment parameters. So nothing should really be generic anymore. And the plant controller, now we should at this point know what the vendor is, and we can start tuning the plant controller gains, et cetera, for the specific system that it'll be going into. And this model is one that we can use for kind of the final interconnection study and the final design evaluation, and even use that model in operating studies if we want to figure out what kind of operating limits we might be imposing with this plant. And then we get to commissioning. So there is usually some difference between the kind of pre-commissioning model and the post-commissioning model. So during commissioning, they will do some tweaks on the model, maybe plant controller gains and things like that, that they found really weren't, for whatever reason, needed to be changed, or sometimes it feels like they needed to be changed. Sometimes it feels like they're changing somewhat arbitrarily, but who knows really. So ideally, this is a really minor change from sort of the final design to commissioning. It's not always the case, but yeah, we need, if there was any changes, we need to update the model, and you may, depending on the kind of how big of a change it was, you may need to rerun some studies at that phase as well. And then also in kind of the post-commissioning sort of lifetime of IBR plant, of course, if there is a system event and you find out that the model doesn't match what happened, what the plant actually did in the system, then there's an opportunity there to go ahead and dig into the model and make some updates on it. And another one is that model maintenance as modeling state-of-the-art changes, right? As Matt said, we have sort of a collective learning process as we go through IBR events and things like that, and we may there may be some aspects of the plant design that are very important, turns out, maybe in response to events that we don't know about yet. Okay, so there's going to be a changing in the state of the art as we see more performance in actual system with these devices. Okay, so I've got a few resources or examples here of entities who have modeling requirements. If you're interested, you can go and check out. These are all kind of publicly available. So Electranix modeling requirements, we initially wrote these EMT modeling requirements, I think over 10 years ago, because there was nothing else there, and we got a lot of really bad models, right? So we need to have some sort of requirements for how to test them, how to make sure they're at some minimum quality level for us. As been mentioned a few times already, there's a NERC recommended model requirements and verification practices document that's very useful, I think. I think if you're looking at adding this process to your interconnection process, you should certainly have a read of that document. It's a very good document. ERCOT MQT or model quality testing requirements have also been around for quite a while. Have a look at those. AMO dynamic model acceptance testing. If you want to go there, it's a huge document, but I think there is a lot of good information in there, but just it's a big one. And then American Transmission Company has a IBR PSCAD model verification procedure as well. That's fairly mature. There's a lot of other examples. Sorry if I left you out. I didn't mean to do it on purpose. And some of these do have their test networks publicly posted as well, so you can have a look at that as well. Okay, one note on data organization, and this fits in a little bit with what Matt was talking about in terms of firmware versions and understanding what changes are made to the model when. It's totally not uncommon to have 4+ iterations of a single plant model as it goes from the interconnection phase to the post-commissioning phase. Sometimes there's more versions than that, depending how many kind of changes are required for that model. And so it's very important to be very organized with your data. So catalog everything that comes in, get revision reports from the plant developer whenever possible. Be very thorough with your testing reports, right? You can see on the right here, this is something from our modeling requirements, model test summary, test date, reviewer, project name, etc. So it's important to kind of be on top of documentation wherever possible. And there are some tools that you can use to sort of help with sort of versioning control, which folks have implemented with varying degrees of success, I'd say. Something like GitHub or SVN could be leveraged because essentially these models are primarily code-based. So you can look at essentially differences in the code of different versions of the model. Some aspects of the code, right? A lot of it is going to be black box and you can't see what's going on there, but you can see parameterization might be, you could easily spot differences in parameterization of the model, for example, with something like that. And then the last one here is that if you want to take this process kind of up one level yet more, is to, as soon as you got a model, you did your kind of intake process, whatever that looked like, and let's say you're happy with it, and you can now, so that you kind of deem that as an accepted model, you can do some preparation for that model that is going to make it basically it's going to be easy to integrate that model into a system study when you get to that point. So you can put some kind of hooks in the model that you can call it very easily from sort of a bigger system case, and you can store that sort of prepared model in a database of tested, ready-to-use models. And then when you go to do your interconnection study, you can have a process for kind of fetching those models and utilizing them. So so there's kind of an automatic procedure you could follow there, but that's kind of sort of an idea that we've been workshopping at Electranix, and I think some other folks are thinking about a process like that as well. But it's kind of it's kind of the last step if you even feel like you needed it. So okay, what's the process right now? We're gonna keep going, chugging along? Okay, awesome. All right. Okay. Okay. So let's recap a little bit what we talked about so far. So Julia laid the stage for why we need EMT models, why we need EMT studies. I talked a little bit about how to collect those models and how to make sure that you're confident in those models, that they're accurate and they're going to be usable in your system study. And now let's talk about the mechanics of how that system, what the process is of constructing that system model and how you're going to actually utilize these IBR models that you now have confidence in within the context of a system study. So when we're constructing a system level model that we are going to use for study, right? There's a few kind of big points that we need to think about when we're constructing our system level model. First one I would say is how big do we need to make that system model? So this is going to be dependent on what you're looking for in that study, even in large part. The next big question would be what models you need to include in that area, right? So the first one would be how big do you need to draw that circle, right? So how big of an area do you need to capture within your EMT system model? And the next question would be, okay, we have our circle, we're pretty happy with the extents. Now, what do we need to put in there? What kind of representation do we want to use for our transmission system and our IBRs and loads, etc., within that circle? Third point would be what are the mechanics involved in actually creating the system model? Okay, is it a manual process? Is it an automated process? What does it look like? What are the options out there? And then finally, is it correct? Right. So there are some checks that we can do to sort of verify some aspects of the EMT model that we've created. A few things to kind of just keep in mind as I talk through these points. There's going to be a lot of balance between practicality and accuracy. Okay, you're going to be able. There's definitely a line where you're going to have to say that the model is good enough, and going beyond that is going to cost you a lot of effort for probably a very small incremental gain in accuracy of the model. Okay, so it's really an art form, I would say, in some sense, to figure out where to draw that line, without sort of spending a lot of resources with kind of minimal gain in accuracy. And then just, there's some realities that we have to deal with when you're putting this model together. We don't have all the data that we would like to have. We don't have test reports of every transformer that's going to be inside of your KEP system necessarily. So, you're not going to be able to get the saturation curves right for every transformer in your KEP PSCAD system necessarily. There's timelines involved. You don't have an eternity to put together the model either, right? There's these kind of external factors that you have to deal with. There's budgets involved, so you can't spend have 10 engineers working on this at the same time, and will quickly eat up the budget, right? So the first thing we need to answer is how big of a KEP system, how big of a system we need to include in our EMT model. So Matt mentioned this already. I think the EMT model runs at a very slow time step, and it has a lot of detailed, complicated models in it. So it's really not going to be feasible for you to run a full interconnect within your EMT system. So we're always going to have generally, we're going to have constraints on that system that we're only going to model a portion of your system. We're not going to include the full thing inside of the EMT model because it would just not be feasible to run an EMT model with that many buses essentially. So we talked about, Matt talked about this already. So the size of the system that you're going to have, that you're going to need to model is going to depend on what kind of phenomena you're interested in studying in. So for the kind of like fast transients that EMT kind of has historically been used to study, we really didn't need a big system. So we essentially would limit it maybe to a few buses for something for something that happens very quickly, and we would we would care a lot about the detail in that system. We would make sure to get, things like stray capacitances and things like that modeled correctly. These things start to have a big impact on very short timescales. But if we're looking at slower phenomena, something like a dynamic performance study, then generally we will want to model a larger system, and we don't necessarily want to focus so much on a tiny portion, because it's not, it's not feasible to add that much detail to a bigger system necessarily. So the process of determining, the KEP system that you want to model is, I would say, part science and part art. And this is an area where there's a big gray zone, okay? And there's not necessarily, the program isn't going to tell you when you did it wrong or when you did it right. There's no green arrow, green button that lines up, hey, you did it right. That's not how it works, unfortunately. So really, we just have to think about, what are the risks of making the model too small, and what are the risks of making the model too big? I think that's a nice way to frame it in. So if you made the model too big or too small, sorry, let's start with that one. What are the risks involved? Okay. So if you're missing some key dynamics within the system, right? So if you have an IBR plant and then maybe 2 buses away, there's a huge StatCom. And if you want to truncate your model at 2 buses for some reason, then you're missing the dynamics of that huge StatCom, and your study is not going to be very useful at that point. If you didn't have a model, for example, for that StatCom, it's not a reason to just make your system very small. We need to think about the performance aspects here. So there's guiding principles we can think about in that space. We can think about coupling between devices, and we can use that sort of concept as a principle for determining whether we need to include key dynamics of nearby devices. And I'll talk a little bit more of that in one of the next slides. We know that the network equivalent, so we're going to have some portion of the system that's kept and some portion of the system that's not kept, right? And the unkept system, typically we're going to have some sort of network equivalent. And that network equivalent is generally not frequency dependent. It's just like a matrix of admittances, essentially. So things like capacitors, they just get netted out inside of our network equivalent. So if we put those network equivalences too close to our study area, we're not able to, those network equivalents are basically having a big impact on the performance of the KEP system, essentially, which is what we want to avoid. So I always want to try and push the network equivalences far enough away, they're going to have minimal impact on the outcome of the study that we're considering inside of our KEP system. And of course, that idea is tightly coupled with the sort of frequency response of our KEP system, which I'll go over in the next slide as well. Okay, so let's say we're happy with sort of those 2 small risks. Okay, we decided we got the key device dynamics, we got the network equivalent kind of we think reasonably far enough away, and the frequency response is maybe kind of what we think might be good enough. Now we kind of have this big gray zone. Okay, so where do we go from here? Do I make the model even bigger? What's appropriate? And so there's some principles we can think of within that sort of gray zone in terms of where to cut off our KEP system. But just keep in mind that there is risks. So you might want to think, oh, I'll just make my system as big as as big as I can, basically. But there is obviously some risks involved in making the case too big. Is that the simulation will become very slow, and there'll be a big modeling burden because you're now including a lot of transmission level elements within that system. So it's not, there's no downside. There is definitely downsides of making the system too big. It just becomes less usable, right? So and that's a reality. You may think, okay, it's slow. It's going to be slow whether it's 200 buses or 500 buses. It's in the category of slow, but it does make a difference. Okay, that 500 bus case does run a lot slower than your 200 bus case. So if you didn't need to make a 500 bus case, you shouldn't really make a 500 bus case. Okay, so that's sort of some constraints there to maybe think about. All right, so we touched on this a little bit. The frequency response of your system that you're modeling in your EMT case is important. So one strategy or kind of method you can use to check how the frequency response of your network is changing based on how big the system is a method where we basically will incrementally increase the size of our EMT case. In this case, I've gone from sort of a focal point growing like 5 buses away, growing 7 buses away, and growing 9 buses away. So we have kind of 3 different sizes of EMT system. And I did a frequency scan of this system to see essentially how the frequency domain impedance would be changing based on the size of the network that I'm considering. And if you'll follow the colors here, so the 5 bus away case is the blue one, and then 7 is the orange, and I think gray is the 9. So you can see how those things are, there's frequency ranges at which they're very well aligned, and then there's some frequency ranges at which they're really not that well aligned at all. So basically like up to like 150, pretty well aligned. Beyond 1000, pretty well aligned. But within there, we get the kind of location of the resonances roughly right, but the magnitudes of the resonances vary a lot. You can see the 5 bus away case has a very sharp resonance at like 900 hertz or whatever, and that actually gets toned down quite a bit as we go to 9 buses away. So there's situations where these differences will make a big difference in terms of the results that you're seeing. The exact kind of like location of those resonances and what their shape is. It's not the case for every study that has a big impact, but depending on the type of study, it can. One thing to note here is that the aspects of the system that really drive the differences that we're seeing here is the shunt capacitance and or series capacitance that we're capturing, okay? Because as I mentioned, in your network equivalent, generally those C's will get lumped, will get netted together with your L's and will kind of disappear. So if you know where, for example, your kind of very long transmission lines are and where your big shunt capacitor banks are located, then you can do kind of a selective grow out of your system. You don't always have to do this sort of brute force method where you're just taking like 1 bus and like everything that's 5 buses away, right? You can definitely be selective within that. Within those parameters, you can maybe take out some of the distribution buses, which aren't going to weigh in as heavily on this sort of impedance spectrum. So you can think of it, like not every bus is created equal when you're considering it in this frequency response space. And sorry, I didn't really finish this thought, but the idea is here where you could, keep incrementally increasing the size of your system until you see very minimal difference essentially in the frequency response of your network. And at that point, you could say, oh, I'm basically happy with how it's looking, and we'll keep it that way, right? You won't always get to that point where you're happy with it necessarily, right? Like for example, here, even 7 to 9 buses away, there was quite a big difference there. But at the same time, 9 buses is already like 700 buses. So that's like a pretty big case. So there's a, this is going to have implications in terms of how long it's going to take that model to run, right? Which is going to impact how long your study is going to take in the longer term. All right, so we've got a good idea of a few ways that we can figure out how big we need to make our system model. Now I'm going to spend some time talking about what kind of detailed models we should consider within that system model, okay? So we figured out how big our circle is that we've drawn, and now we need to think about what kind of detailed models we're going to start putting into that circle, right? So the big one is, of course, IBR models. And you're always going to have some region where you're interested in the dynamics. And so there's some IBR plants that are going to be a given that you're going to have to model with a detailed IBR model, right? They're the reason you're doing the study, right? And now in the region, as we look out further, zoom out a little bit from that sort of very focal point, there's going to be potentially other IBRs in that system, right? And one thing to keep in mind is just because an IBR plant is within your KEP system doesn't mean you necessarily have to model it with a detailed model. If it's at the kind of extremes near the boundary, and if you and based on the kind of coupling that you see between devices, there's not really necessarily a lot of benefit in including something that's near the boundary of your KEP system. So one concept you can think about to determine this is the idea of coupling. Okay, so we know that when we're thinking about IBR plants, really what we want to diagnose is whether there's going to be a risk of interaction, right? That's essentially why we're doing the study most of the time with IBR plants. We're thinking about ride-through and things like that too, but a lot of the time we're thinking about risk of interaction. And the risk of interaction is going to go up, generally is going to go up when the system, when there is strong coupling between devices, okay? And one mechanism we can use to determine whether there's going to be strong coupling is whether they're basically decoupled by a strong grid, okay? So if you imagine you have your big EMT case and somewhere down the middle, you have a very strong region, like a very, 345 kV line that's really kind of sort of splitting your KEP system into two parts. You can generally, depending on what things kind of look like, you might even be able to say, oh, actually, I thought I had to model this all in one case and study it all in one case, but really I could actually maybe get away with using two separate cases because the dynamics of the two sort of like halves of this system that I'm looking at are very much decoupled by a very strong sort of intermediate region. So you could see that, dynamics on one side are not necessarily going to influence the dynamics on the other side. So there's sort of some decoupling between these two. But on the flip side, we're looking at, for example, in this diagram that we have here, if we want to study G6 here, one of the ones in the bottom right corner, we want to think about whether we can sort of lump these plants together into a group of plants that might be experiencing a weak system phenomena or something like that as a whole, right? So, and we have to think about this not only in steady state, but also considering outage events, N-1 and N-1 sort of events. So, if we take out some of those lines connecting this sort of like bottom right cluster out to the rest of the system, then yeah, they sort of look like they're going to be, kind of like almost radial connecting through to the main system. So we can think that there's going to be pretty strong coupling between those plants. So we should probably model all of those in the bottom right corner. And then if you look at something like one of the ones on top there, maybe G9 or something, it's gonna, you might keep it, you might not, right? Kind of depends on maybe what your system strength is at kind of that the sort of overlapping point at where that line comes in. So there's kind of nuances involved here, and it should be very much topology dependent, whether you're going to include one model or not the other, right? So yeah, there's this is a deep rabbit hole. We can go really down here, but there are some technical references that you could look at. Connection of a C-grade connection of wind farms to weak AC networks, and ERCOT Panhandle of Renewable Energy Zone report are really great examples where they lay out some of these concepts, and they also talk a lot about screening metrics, which is something I haven't really touched on yet. Another thing we could go way into the weeds on. But there is some metrics, some sort of, I guess, semi-automated type ways that you could figure out whether these plants are going to be interacting as a whole, or whether you might be able to consider them somewhat independently, and how severe of an interaction they might be having, I guess. Okay, so moving beyond the IBR models and talking a little bit about the transmission level elements that you may consider including inside of your case. I titled this as detailed models included, and just to give a little bit, zooming out a little bit on what we mean by detailed in this context for transmission level elements, it's really detailed relative to a model that you could derive based on, for example, just the load flow data, right? So if you have, like your PSSE case or whatever, and you have a transformer and you have the R and the X, and you have the voltage levels, you can use that to create a transformer model inside of an EMT program. It just won't have, some of the details that we might be, that we could have inside of the EMT program, right? So if I jump down to that transformer one, in the EMT program, we can, winding configuration is of course very important to get right whenever we can, but also saturation. It's something obviously that we can't model in, or that we typically don't model, at least in sort of the phase domain. So you're not going to get that data from the load flow information. So this is going to be detail that you're adding on top of information that's within the load flow data for these transmission elements. And I should say that it doesn't, you don't necessarily need to apply the same rules for every element that's within the kept case. Okay, so if you have some focal area again that you're looking at, that you're interested in, maybe you don't need to include all these details in terms of transmission lines, transformers, etc. You don't need to create detailed models for everything inside of that that kept system. You can focus that modeling effort to where it makes the most sense, and that's going to be kind of probably where those IBRs are that you're kind of specifically interested in the performance of. So when it comes to transmission lines, we have kind of three main models that we usually will be able to pick from. You can have a pi section model, which is kind of just like a lumped parameter model, really only suitable for short lines most of the time. And we can have a Bergeron model, which is like an infinite collection of pi sections, essentially. It's a traveling wave model. And then we can go all the way to the frequency dependent line model, which takes into consideration the actual conductor information, the actual geometry of the tower to create the model. And that's kind of the best one out of these three. So you can see in the diagram on the right side, essentially we have this is kind of a pretty old figure, but it does kind of illustrate the point a little bit. So we have on the first graph, we have basically this is a simulation response compared to some field measurements. And so in the first one, it's a simulation done with a Bergeron line. In the next one, it's a frequency dependent line model. And in the bottom one, it's the actual field test measurement. And you can see that in the Bergeron line model one, we have some high frequency components there that are quite jagged, and we don't see those in this sort of actual field test measurement. So this is not uncommon. Bergeron models don't really take into consideration the skin effect of the conductor. So their damping is at high frequency is going to be generally underrepresented. So that's kind of something to keep in mind, I guess, with transmission line models, is that you can have, it makes a difference, especially for damping at higher frequencies, which model you choose. Transformers, of course, we talked a little bit of it. So winding configuration is great if you can get that right. It affects, your zero sequence currents and things like that you're going to see in your EMT case for fault events. And saturation, yeah, whenever we have an excess amount of flux in the transformer, we're going to have some saturation phenomena occurring. So if we have that information for this transformer, then we can put it in and get a more accurate model. Loads, similar sort of thing. We can have zip loads, which are just constant impedance loads, or modes that have some induction motor load content, like a C load or a CMLD. And then we have sort of non-generic set of models, which would be like specific for an arc furnace, or maybe like a data center load, that is like extremely volatile or something like that. So, we kind of have to make a decision there on what we choose as well. Yeah, lots of trade-offs between simulation time and complexity. Synchronous machines, this is what I would call in our non-IBR generation sort of. So typically we can get away with using standard library models for synchronous machines. We might have some custom exciters or custom governors and things like that, but for the most part, these can be standard library models. All right, so a little bit about how to actually go about constructing the EMT model. So we decided, this is the area that we want to model in EMT. We've decided these are the detailed models that we want to include in our system. Now, what are the actual mechanics involved in creating our, basically taking these various puzzle pieces that we created and putting them together into a cohesive simulation that we can run. So there's two main approaches here. So I should back up. This generally is not done manually. It's a huge effort, and it would take a lot of time to do manually. So this is usually done in an automated manner using commercially available tools. One way would be to essentially take pre-solved data from pre-solved load flow data and a database of detailed models, and put those and give that information to some sort of conversion tool, and it'll spit out a EMT model for you that initializes to the set points that were that you had from your load flow data. So this would be your load flow data from PSSC or TSET or whatever, and it can solve to essentially it'll initialize to those conditions. The other method would be to utilize load flow solvers within the EMT program itself, and there's pros and cons to these two methods. Utilizing load flow solvers within the EMT program will allow you to do things like take a line out and then resolve for the initial conditions within the EMT program, which is helpful. But then you also have the downside of perhaps misaligning with your database of load flow data, for example. So you have multiple databases you have to manage perhaps if you go down the kind of method 2 route. So there's kind of pros and cons to the methods, but there's this is kind of what's out there. Here's just an example kind of process of what a conversion to EMT might look like. So solved load flow data, kind of in the first line, it's kind of your first data input. And then the next kind of big blue block down there would be a component database or library, which would contain your IBR models and any system component models. And then on the bottom, you would also want to input your study area selection. You'd jam all that into a conversion tool, and it will kind of auto draw an EMT case for you. It'll connect all the various pieces together and put in the network equivalent. Here's just an example of what a database might look like that contains generators, wind farms, loads and transmission lines, etc. And here's what maybe the inside of one of these blocks that represents a generator might look like. So we have a generator model, an exciter, and a governor, and we can actually back calculate the state variables of some of these controllers based on the terminal conditions, and that'll enable us to get kind of a flat start in our simulation. One note in referring, in terms of initialization, we mentioned a few times maybe, unlike RMS simulations, EMT models typically initialize from 0 voltage and 0 current, so they have to ramp up within some time frame. Usually we say we want these models to kind of give us a flat line within 5 to 10 seconds. And it's important that they initialize quickly because these models take so long to run. So, even just getting to the stage where the model is initialized can sometimes be, like half an hour of simulation runtime. We can do things like snapshots as well if you're used to transient stability study. But there's sort of, the models have to be compatible with snapshot assembly, so it's not always an option. A few notes on external system modeling. So we've talked a lot about what goes inside of that circle. Now let's talk a little bit about what might go on the outside of that circle to represent the external system. Let's say, for example, we have this area in kind of blue or whatever that we want to model in EMT. Then we would maybe we would tell a conversion tool that, these are the buses we want to include in our EMT simulation. It says, great, that sounds good. I'll make an EMT case of your network that you want to keep. And then all of your boundary points, let's say there's n boundary points, it kind of sends those all to a network equivalent. And then the network equivalent will do essentially impedance matrix reduction of the external system. It'll compact that whole external system down to an n by n network equivalent. And so you have some diagonal and some off diagonal impedances in that network equivalent, which is kind of what I'm showing on the bottom there. In this case, I'm showing a 3x3 network equivalent here. These network equivalents can be huge, right? You can have sometimes, over 100 boundary buses or something, in which case this network equivalent would be really a huge page. The network equivalent can either be a dynamic network equivalent or a passive network equivalent is what we would call it. So you'll remember that our network equivalent has voltage sources within it. Kind of like at each of these n boundary buses, you'll get a voltage source within the network equivalent. And that voltage source, that it was going to have an angle magnitude, a voltage magnitude and angle within it. And we can choose to have that angle fixed, or we can actually choose to change that angle based on some external simulation. So for example, you could do a co-simulation between a transient stability tool and an EMT program such that the angles of your network equivalent will get updated by the combined effect of both simulations running simultaneously, which is what we call hybrid or co-simulation. All right, so we're almost out of time here, so I might skip 4 more minutes. Okay.
4 more slides.
Oh, 4 more slides. Okay, 0 minutes. All right. We'll get through these as quickly as we can here. So yeah, a couple slides on hybrid or co-simulation. I'm gonna cover this relatively fast, but yeah, essentially it's a mechanism that allows you to run an EMT simulation and a RMS or phasor domain simulation simultaneously. So you'll basically have, in the EMT simulation, your external system is modeled with a network equivalent. And in your RMS simulation, you'll take the part that was an EMT and remove it and replace it with a network equivalent that represents the EMT portion. And then, you'll take these two cases and you'll run them in lockstep, essentially, and they'll exchange information at the greater of the 2 time steps. So they'll update each other on what the quantities should look like on either side of the boundary. The typical use cases for hybrid or co-simulation are in scenarios where we have a high power flow through our EMT system. And if we interrupt that power flow, you can imagine now, in your phasor domain simulation, if you interrupt that power flow, the angles are going to change in the whole region, right? All of the buses are going to get some new angles, and they might be really big changes. Now, if we do that same thing inside of our EMT program our EMT simulation that we've constructed, we take that line out, and the angles at our network equivalents actually don't change, right? So if they're kind of fixed angle, so we can have essentially this amounts to a difference in the post-fault power flow through your EMT system. So if you're very worried if that's going to be really important for the study to get that post-fault power flow exactly right, then you might use a co-simulation or a hybrid simulation to get that sort of changing angle effect. Another typical use case would be if you're worried about inner area machine dynamics. Those generally won't be picked up inside of your kind of a pure EMT program because you're just not modeling a system that's big enough to capture that. So if you want to get those inner area dynamics, you're worried about those big swings, then you need to go to generally need to go to a co-simulation. And then the last one here would be, uncertainty. What don't you know, right, about the model? So how do you get that sort of warm fuzzy feeling about your simulation results that let you know you kind of captured everything the best that you could? So if that keeps you up at night, then yeah, go ahead and at least run a sensitivity on your system to see whether it makes a difference, right? If you have confidence it doesn't make a difference, then good. You don't need to do that in the future anymore because it is a modeling and simulation burden to add that co-simulation. Okay, very briefly, how do we know the model is right? How do we maybe do some verification on it? Of course, we can look at the power flow inside of our model, especially the initial power flow, and compare it to what we would have inside of your load flow program. We can get this power flow to line up very closely if we're very careful with our initialization. We can look at short circuit currents. If you have short circuit levels that you're expecting based on your protection software, or maybe even your phasor domain simulation for a three-phase fault, then you could do a comparison of that sort of fault current as to what you get in your EMT simulation, if you just apply that kind of same fault and measure the fault current. You can benchmark against transient stability where applicable, right? So remember, there's going to be inherent differences between the tools, sometimes inherent differences between the models. Best case, sort of the best use case, in my opinion, for this is to benchmark the sort of local electromechanical modes against each other. Hopefully, those are going to line up pretty good between EMT and your dynamic phasor model. Frequency response characteristic, we kind of talked about this already, how we can keep growing our network to see when things start looking more accurate, essentially. Field validation, we talked about as well. So if you get event recordings from your system, you can play those back into not only your IBR model, but you can also do some things to maybe check the performance of the actual system components as well. All right, I'll skip this one for now. Okay. Coffee break.
So there was a lot of material to cover. We'll take 15 to 20 minutes for Q&A before we break for coffee. So just come to the microphone, introduce yourself, and feel free to line up if you want to ask a question. Go ahead. It's on the top here.
Can you hear now? Yeah. Thank you. It was very nice presentation. This is Purya Astero from ERCOT, and I have a question about the inverter models, the accuracy that we need, and DC bus. In all these three presentation, presenter talk about the importance of the DC protection. Some event from DC happened in Texas, and then the accuracy of the model. Then we know that the system operator gathering this EMT model, but with which accuracy is correct? At least two main methods is there: average modeling, that is faster, and then the detailed switching of the legs, but it's slower, but maybe more accurate in the DC side. And at the same time, I don't think that for operator and OEM is very practical to have several models for different study, because then this model should be checked that have the same result and all these things. So what's the solution or discussion on that if we have time?
Do you want to start?
Yeah, go for it. Or
Well, I thank you for the question. Is this? Can you hear me? Okay, yeah. So a couple of great questions that I picked out in there. Maybe I'd start to take it apart and then we can discuss them. So on the DC link side, I think it's first important to acknowledge that not every IBR has a similar looking DC link, right? It depends on what the technology is, right? And so for maybe on the simpler side, a battery system, it has a DC link that looks one way. On the PV side, the DC link is kind of, more power electronics, if you will, but just silicon panels. And then on the wind turbine side, it can get quite a bit complicated, and depending on whether type 3 or type 4. And so whether and how much detail deserve to be on the DC link side of your IBR, I think is in part dependent on the technology. That said, what is common is that if it impacts the performance in a material way at the AC, at the grid connection side, then you need to have that in there. And so, for instance, if you do have a technology where you have trip thresholds based on DC quantities, you need to have enough representation there to capture that. I'll start there, or maybe pause there. And then you also mentioned the difference between switching models and average models. And maybe I'll hand it over to Lukas if there are any other comments. Or...
Yeah, switching model versus average model. It's a great question. It's a debate I think we've been having for a long time. I think you know, I don't know. I've heard multiple kind of opinions on this. Like some folks say, okay, we have a switching model, and if our switching is not ideal, you know, we might have some phenomena occurring at lower frequencies. But the thing is, our switching is ideal in the programs, right? So generally, switching is going to produce impacts at really high frequencies. And in our opinion, is probably not going to have an impact on you know, things that happen at the time frame of a transient stability study. But yeah, that's essentially my thought on that. But great question, though. Yeah.
Did they cut you off already, Russ?
There we go. Okay.
All right. we'll give
Russ
you a chance.
Fulbright, Polaris Systems Optimization. EMT tools are obviously a great resource to do lots of interesting and important work. But I wonder if we're using them the right way. We seem to focus on the input side. We have a new plant come along. We want to study it, see how its effect is on the grid on a local area because of the difficulties of doing a large area, so we're not capturing the system impacts. And I'm wondering if it's the right process. Can we turn this around, and how difficult is it to say, can we use EMT studies to tell us what we want? So that instead of having it applied once a plant has already been designed or some prospect has been developed, to say what we would want from the plant at that location, or more generically, so that the developers are not having to cast about. And we're not getting ourselves into these exhaustive studies and slow interconnection queue processes. John Simonelli gave a great example. I'm going to steal. I mean, I hope I'm not stealing his thunder, but he said, it's like going to Amazon. You need a pair of sneakers, right? Do you go and you tell Amazon, I need, 10D size of sneakers in white, right? You don't tell Amazon you need a pair of sneakers and then have them send you 100 pair of sneakers, and then you sort through and figure out which one fits, right? You have the specification up front. Can we use EMT to get to that point? And I think I've also heard that in Europe they do it differently, and then maybe in Europe they have that process already, and maybe someone in the audience here that's familiar with that can speak about that. But I think, can we redefine the process to do better engineering?
At a high level, I think you need to do a little bit of both. I think what we're seeing now is as people start working on defining specifications for grid forming inverters, that's maybe a little bit what's happening. So people taking parts of the system, say weaker part of the grid, modeled in EMT, and then they will test what kind of capabilities from inverter help to solve certain issues, and then kind of that feeds back into specifications for grid forming inverters. So that's one part. But otherwise, I think maybe that would have been possible with kind of simpler synchronous machines before, but with inverters, there is so much flexibility and so much differentiation into how like different capabilities can be implemented from the inverter side that I don't think that's possible.
But that's converting an advantage into a disadvantage because of all that flexibility, right? If we said, the flexibility is great, it can adapt as the system needs change. When the system decides that it needs something different, like we would do with, say, governor response on the system in the past, we we could make reevaluation and say that the system needs something different, then everyone could change. And inverters can do that also, just like we could in the past with governors. So why do we make everything bespoke? You know, why don't we lay out a design criteria? And maybe we won't get it right initially. There'll be holes in it, but we can figure it out and get the holes filled in and get to a point where build to this standard, and the process for connecting is quick and easy because we don't need to do those studies. We've already done the studies.
Yeah.
I think it is kind of, that's the thinking, but I think it's still complicated. So like, I mean, there are requirements even now, say a EEE 2800 has already like up to here detailed requirements, but still how you achieve this requirement can be different. You cannot go in and describe every, I don't know, control parameter, every control loop and function that is there. And it's also like, it's a patent thing too, right? So you have different technologies and somebody invents something and they patent it. So then the other manufacturer has to go around this somehow to implement the same capability, but not using the same method that somebody who patented it is using. So there is this layer too. And then say, for example, you mentioned like, oh, we can go back and change. But in say in ERCOT, for example, in 2800, they're trying to implement right now, and they have so many inverters now that they are looking backwards and saying, well, I need inverters to do this and that, even those that's already there. And theoretically, yes, it's possible, but logistically, it's very complicated.
Logistically, it's complicated because
every generator owner needs to now get in touch with inverter manufacturer and talk to them what it takes to make changes to the control loops to now perform to whatever ERCOT wants them to do.
Well, yeah, that's not the process you'd use. You'd say that the standards authority would say this is what we need generically, and then inverter manufacturers would already know that, and there wouldn't need to be that loop.
Yeah, I think that is the gap that 2800 is trying to fill.
Yeah,
Right.
it'd be good if we had more discussions about that, because it seems to me we're going to kill ourselves with the way we're going now, and we're not going to get things done.
Yeah, I think we're having a bit of those discussions though.
Okay.
Yeah,
And like-
maybe.
Thank you.
Yeah, no, and it is happening in the 2800 circle as well, right? Like, I mean, so, you know, there's a huge range of operating conditions which an IBR can face in the system. Like the short circuit ratio can go from 5 to maybe like 40 or something. So it's a big range, and you can have, you know, large ranges of impedance spectrums, right? So during the initial design evaluation, like something like what is even what is proposed in 2800, it's never going to be able to fully encompass all of the possible grid operations. So there's always going to be surprises. Like I don't know if there's really a way to get around, you know, being surprised at things in operation or at the interconnection study level, just due to, you know, everything is software based and it can interact in unexpected ways. I take.
Thanks. Brian Plumtier from Unruh. First off, thanks for the great overview. It's been a really great place to get started. And I have a couple of sort of fairly basic kind of almost process type questions, I think mostly to Matt. One of them, these kind of go together, is the idea that the black box models seem to be certainly a common thing with the EMT space. Like, are those interoperable among tools? Like, really basic question. And then sort of related to that is there's this effort around, hey, we need to keep things updated. Are there processes whereby like every year someone sends an update? I kind of get the sense that sometimes it just comes at the beginning and you keep having to beg for it later, but I don't know, maybe I'm wrong. So curious on those two. One other after that.
Those are great questions. Actually, I think Lukas and Julia may be really well suited on the interoperability, and then on the updates side, we can definitely talk to that. Yeah.
Yeah, I guess on the interoperability side, it depends how the model is constructed. You can, you know, Matt touched on this. There's a joint IEEE CGRE initiative that is working to harmonize the interface between real code models such that they can be used between various EMT software tools as well as actually phaser-based software tools. So there's initiatives in that direction, but there's nothing, you know, adopted at a wide scale at this point, unfortunately.
I think also just an appreciation of that maybe you don't get from the phaser domain tools we're used to is like, are your time steps coordinated? right, for these things. And if this model has to run at 16 2/3 and that model has to run at 10, where can they meet? Do they have the same Fortran compiler? Like there's all of those things that are just not even engineering aspects. They're just part engineering, but there's also a lot more software aspects that make the practical realities of, doing a single machine infinite bus. It's like, okay, yeah, I get this. This is great. And then you get two of those together and you're like, maybe you get lucky. And then you get a system-wide model and it becomes a real challenge. So I think that's a very real aspect of that. Thank you for highlighting that.
Just in terms of updates of the model, how frequent, if, just to fill in a little bit, in 2800.2, we're still working it out. So basically the wishful thinking is every time something changes in the model, and I think we have it there in the draft kind of high level, every time something changes in the plan that can affect the performance of the plant, you should update the model. But on the other hand, we're now talking about things like augmentation of battery storage, where say Tesla is augmenting on the AC side, and they are doing it basically on continuous basis. They are adding inverters to the battery and keeping the output at the same megawatt level as sign generation interconnection agreement. So it is a change in the plant that may potentially affect the model, but is it practical to update model every time they change, swap one inverter or add one inverter? That's probably not. So we're trying to figure out what's the frequency that makes sense. I think also mod 26 NERC standard will probably have some frequency timeline there, but we are still figuring it out.
I guess I'd share on the updates. When would you update the model for a synchronous plant, right? Out of cycle, right? A generator rewind or an excitation system upgrade. I mean, like months-long processes, cabinets moving, right? Big physical hardware. And even then, I'd kind of argue, all right, performance is still, it's not going to be wildly different, right? But with IBR now, it's just a different animal. And you say, okay, well, the hardware looks the same. The thing runs the same. But I flipped a bit over there. I changed that parameter. You did what? Right. Well, which one did you flip? And what did you change it to? And what are the implications? And it's these little things that are easy to dismiss and overlook, more so than like changing out a cabinet or ripping down a machine, that actually can have more dramatic, very dramatic differences in the behavior as viewed from the grid. And so I think it's just that kind of consciousness raising as we're on this big journey here. And what we were used to is just the telltale signs and the markers of, hey, is this important? And do I need to go back to the model? That stuff really needs to be reconsidered. I think it's a great point.
Awesome. I did have another quick question, I think to any of you really, but maybe Mark, was you mentioned, hey, these studies are huge and there's a wide range, and there's a couple that might be a better place to dip your feet in. I was wondering if you could elaborate on, hey, wait, these might be the scale of things you might consider dipping your feet in as you're starting to get more into this space.
Sorry, actually, I didn't catch all of your questions.
Oh, you were talking about, obviously there's a huge landscape of studies, and trying to do this for a very large system with a fairly complex arrangement is probably not the place for folks to try to get started. But you mentioned, here's a few ideas of where you might want to dip your feet in. I was wondering if you could elaborate.
Yeah, great. Yeah, thank you. So yeah, if you're considering getting into this, like where do you start? Where is the shallow end of this pool? And I think what we'd see is, I talked to my own experience, like where I got started with this was on that single machine infinite bus and system and working with kind of one model. And there's a lot of advantages for that one. You can kind of defer some of the complexities of the software and the interoperability a bit. And you can also really test it in kind of that test bench environment and really understand what it's doing and check and make sure that the quality, that the responses, when you hit it with a change in frequency, what does it do? If you hit it with a phase step, what does it do? And sanity check. And I think that's a precursor. That's an important part of the model quality testing that you can't skip that step anyway. And it's also a very sensible one to start with. And as you get comfortable with that, then you start linking them up and building it. And eventually you get to the things that Electranix can do that are very impressive and at very big scale.
Yeah, great question. I just say I kind of got lucky here. You know, when we started doing this work, it was like one plant interconnecting, nothing else nearby, right? So nowadays you guys don't have that. You know, in most systems you don't have that benefit. So try to find one, and you know you can get lucky, but probably it'll be more complicated than that, unfortunately.
All right. Well, we try to get through this last 3 questions quickly so that we have some time to break before
I'm
the next
very
part.
quick to
I think it may be on.
I think it is on.
It is on?
Yeah.
Oh, quick question on administrative items.
Could you please introduce yourself though?
Sorry, my name is Justin McLeod from Excel Energy. Wanted to ask when this presentation will be available. I was searching for it and I would love to take notes on it. And the second question is more technical based. Have you found any best practices in management of the models coming in, storing and making use of as you break your system apart?
Yeah, so to answer the first questions within the next couple of days, you'll find. So the first question was when the presentations will be posted, and the second question was are there best practices in kind of keeping models and model databases, organizing model databases. I hope the guys can answer that. So, but for the presentations within the next couple of days, you'll see them on the where the main event information is, and then it's all recorded and will be posted. Maybe within a month, the recording will be there on our YouTube channel.
Yeah, I guess on the organization bit, you know, make very detailed folder structures, I would say, and, you know, label everything with the date, of course, that the model comes in, and then keep everything that you got with the model in that one place. You can have a lot of issues down the road if you start to keep dependencies for models in different places in your folder structures. So, you know, catalog things and document everything that you can, I would say.
Hi, my name is Jose Lara. I'm from Unruh. I have a question more if you can speak also to like a lot of these processes and things that you describe and a lot of these challenges. From the outside, looks like there's a big software gap in terms of capabilities because we keep trying to create these processes and have to deal with all of these problems because there's a bunch of legacy things that we keep keeping behind. What Fortran compiler do we have? With Delta, does this thing has? Keeping folder structures, which to me is crazy that we do folder structures to keep data models when there's version control technologies out there. To what point all of these pains and problems that you capture are in a big way a technology delay of the utility industry with respect to the software industry? Like having the fact that a firmware gets updated, if you talk to Amazon, if you talk to other kind of industries, say, how do you update your firmware to your hardware? They have continuous integration techniques that they say, the moment a new piece of firmware is created, it goes into continuous integration, runs into a simulation in Modelica, automated, and you can tell if this firmware breaks everything else. Like, why do we struggle so much with software to actually get these things done when the solution is not rocket science, right? We're not trying to send a rocket to Mars. We're in an industry that should be looking at the other industry and say, hey, you seem to figure out how to do complex simulations in complex environments and test them fairly well. And we simply keep in a lot of these kind of complicated processes, outdated mechanisms, and so on. Maybe you can talk to that. Like, to what point do we say and stop dancing around the challenges of the tools that we have that were developed for a context in a particular set of complexities and say maybe these tools that we have developed for these complexities are like a hammer and a chisel when we need now a power tool that has, an actual power hammer to go and bring this building down instead of a chisel and a hammer. So I don't know if you can talk to that part.
I'd love to hear from the vendor panel.
Yeah, maybe we'll leave this for the vendor panel at the end, and maybe if Lukas and Matt want to add something to that, we'll take it at that time. I think it's an excellent question for that panel. Go ahead.
Hi, Will Schmidt from Killier Research. That was a great question. I'm very interested to hear what vendors have to say. I think, yeah, there's right.
No, we keep it till later.
Totally, yeah. Well, I'm definitely very excited. And I think kind of my question is not going to be the same question, but it's sort of in the same spirit, but on the applications, how we're using our models. there's been a lot of like non-engineering type of problems that we have, or non-electrical engineering types of problems that we're running into. And I think this last question does relate to that, but there's this notion of, hey, you can have simple and low fidelity models that you do a ton of modeling with, and then you can have very high fidelity EMT models that you can do fewer studies with. You kind of trade one off, and that really kind of assumes that it's a zero-sum trade, that you're kind of really trading one resource for another, whether it's human or compute. But I think that a lot of things have changed over time for the better. Even on the software side, folks are using version control in some situations. Like Git is very popular now and is actually usable in our industry. And compute has gotten much stronger. The converter controls haven't really gotten that much more complicated to the point that it impacts like the computability of our ability to simulate that. What can we be doing more with kind of the existing technology, or that you're looking forward to being able to like get more out of, so that when we're on that extreme end where we're saying, hey, we can do fewer things, but now like there's like way more resources. You talk about automation, like PSCAD has a Python library now that's pretty strong. What are the things that we can be like, what's the next step here to be able to say, we're already at that extreme, what more can we get out of it?
Yeah, really, sorry, there was a lot there. Yeah, like compute side, let's say we'll start there. It's sort of an exponential race on two sides. Like our compute is going up exponentially, but our grid complexity is going up exponentially. So, we're kind of tied, like always, it feels like we're always tied in that race until we see like a major breakthrough. So, AMD keeps releasing new Threadrippers. Now we're at like 96 core. It's a wonderful machine. We can run a lot of simulations on it, all in parallel and all that. But at the same time, we have to model a lot more IBRs at the same time. So I don't know if we're going to see a breakthrough there in the very near time frame. We'll hear from Paul and from the real time side, like perhaps there's something we can do there with sort of like this dedicated hardware approach, right, to starting to model more bigger and bigger systems in a real time approach potentially, right? There's capability there perhaps. But I mean, I think a main problem is that everyone is in the middle of this, and there's not a lot of folks who really have the time to really take their heads out of the sand and really like look at the problems from a really high level and figure out whether there's a new paradigm that we can use for simulation and for modeling. I think there are some folks working on that, and we'll see what comes out of it, but these things change on a very slow time scale. So I don't know if you guys have any more thoughts on that.
Yeah, I should watch my mouth, I guess. I think that the tools have come a long way, and with Git, with version control, managing the data handling, they have a lot farther to go. But that also moves the bottleneck, and I think the bottleneck still remains a human one and an understanding one, and that is not about to change. And yes, that's not a reason to not pursue the software and kind of, do what the broader software industry has done to other industries and bring that in. But that's not a panacea for the problems that we have. I think if you go out, so I have to remind myself of kind of the bubble that I live in and that this group, I think, lives in, and that we really see these challenges and understand them, but there is a great big world and industry out there that is unfortunately not here, right now in this week, today, and those folks need to be brought along and really understand. And so it's not that, do we need to figure out how to throw more processing or compute power at that? It's, do we have the understanding more broadly? Can we bring more of the folks along with us in the transition to understand the challenges and to give them the coaching and make the tools available, just the ones that exist today, and get them started. And I think that's where, if we're looking to really get more out of this and do this better, make this transition better and smoother, I think that's where we really need to focus the effort, is more on the people and the understanding and bringing in the best practices that we have today.
Just to follow just on your point around the human bottleneck, do you mean like the human bottleneck being there's just really not enough people who are really thinking about this and understanding it, or hey, like there's still like, we need to have humans that are interpreting this information in some way physically. And so like, I'm asking like, what is that human bottleneck really, that, is it something that we just solve with more people that are getting trained, or with more insights that are available for free to humans to be able to do kind of more of those higher order analyses rather than the boring little stuff?
Yeah, I mean, it's for a lousy answer, like, yes, it's all of the above. I mean, and I'm sorry, I don't mean to reply that way. Imagine if we solved that software problem, right? Or like, and no offense to, the software vendors, but imagine the things that you guys are pointing out and saying like, okay, compute is no longer a problem. Interoperability is no longer a problem. What is the problem? And it's understanding the data. And yes, you can get answers faster, but are the answers correct? How do you know that they're correct? How do you convince other people that really also bear the risk, that they can trust it and that they are correct? And that, the software is merely the tool, but it doesn't just get the whole job done. And so even if you solved that part of it, you still need to make sure that you have the engineering judgment that's applied. And yes, can that be made easier and get the right data in front of you in the right format and make that easier? Yes. And I think we should continue. We've come a long way there, and we should continue that. I think that's really, maybe then the answer that I'm arriving at is, what we really like is to get that data more easy to handle, to work with, to keep track of, and to display so that human judgment can be applied more efficiently. I think the tools like Git and the other developments that the vendors have been introducing are really great steps along that way. And given that we are going to be, I would think, human bottlenecked on the human side, it's just making the humans more efficient. Yeah.
Thank you.
All right, so we ate up into the entire coffee break with the questions. So let's say we take 10 minutes for, stretch our legs, get coffee, grab some snacks at the back, and come back.
Up a little bit on what we talked about in the last section. We talked about how we can create our EMT model, how to come up with the kind of the KEP system, what to put in it, what kind of models we want to put in it, and whether, how we can figure out whether it's accurate or not, or verified at least. And now we're kind of to the point where, logistically, we're going to start trying to run some actual simulations inside of this model. So this is where we maybe start thinking, probably you start thinking about this earlier, but we'll touch a little bit on, scoping contingencies, scoping kind of which base cases, for example, you want to run, and also just some practical considerations related to simulation. So when it comes to scoping your contingencies, it's really, it's a very critical part in an EMT study. And main reason is that you want to be very selective in which contingencies you want to run, compared to the paradigm of your phasor domain simulation, where you maybe, you're just like, oh, run everything, right? Figure out your stability for all your n-1s. For example, that doesn't really transition to EMT very well at all, because our cases take so much longer to run. So we want to be very selective in this procedure, and we need to ask ourselves what are we looking for inside of our case, right? What's our concern? So we talked about a few possible concerns already. So series capacitors, weak systems, interactions with specific devices in the network. So we should really be focusing our contingency list to, target these specific things that we're looking for, okay? So a weak system study, for example, we want to look at kind of, what's the worst kind of case that we can come up with in terms of cutting off sources of strength and perhaps grouping IBRs together such that they're kind of acting in a lumped matter, connecting into one kind of weak system. So again, we want to kind of come up with a minimal set of scenarios that must be chosen to answer the question that you're trying to answer. Okay, and this should generally be done. It's best if you already have your load flow studies and your transient stability studies already done, and then you kind of backfeed those results into your contingency scoping for your EMT simulation. And it's kind of, the notes here, it's an uncomfortable process because you're actually gonna, now if you find something in EMT, oh, you need a mitigation, you're gonna have to go back and rerun all your power flow and transient stability scenarios. So it kind of turns the whole thing into an iterative process. Unfortunately, if you see an issue in your EMT simulation, okay? Screening studies can be extremely useful to help reduce the case list. So there's, on the weak system side, we can look at metrics like short circuit ratio, weighted short circuit ratio. There's more advanced things that you can look at to kind of skim down the number of cases that you're looking at to just be the worst case. And for a scenario like series compensated systems, you can look at radiality factors and things like that to figure out how radial your kind of device that you're interested in is to a series capacitor, for example. So again, phasor domain studies can be used to help select your case list. So you could look at your kind of marginal results from your phasor domain simulations. You could look at cases where you had criteria violations or where we had unsolved cases. Those might be kind of things you could use as hints for those scenarios that, phasor domain maybe wasn't the appropriate tool to study those specific contingencies. So those are the ones we may want to bring in to study in the EMT space. And a note on sort of dispatch scenario or load scenario that you want to study in EMT. It's not really, we can't generally say that, for example, a light load case is going to be worse than a peak load case. They're going to be, they're going to be essentially different things that you're probably going to see in those cases. A light load case, you're going to more likely to have higher voltage transients, as your kind of like transients aren't necessarily damped by a lot of load in the system. And also in your light load case, if you're pushing your IBRs to your maximum power limit, you're probably going to have to turn down or maybe even shut off some of your synchronous machines in your study area, which is going to lower the strength of the network even more. Yeah, these other ones we generally kind of hit already. Okay, so moving beyond contingency scoping, we'll talk a little bit about simulation speed. We've hit on this a few times already. So ENT simulation generally they run very slow on the system level. For a context of scale, if we are running 10 seconds of simulation on even like a medium-sized system that has a few IBRs and a few DTLT lines and maybe a few load models in it, it can very possibly take more than an hour to run that simulation. Okay, so it's slow. Reasons being small time step, switching models if you have them, complex models. There are some things we can do to make the simulation a little bit faster, a little bit more manageable. One very common strategy is to segment your case into your big EMT case into multiple smaller pieces. Okay, and we can call this parallel processing, is what we usually refer to it as. And I've got an example of that shown on the figure on the right here. So this is an example from a study we did in the ERCOT system. You can see all the kind of green boxes around the outside. Those are all individual IBR plants, all running inside of their own EMT process essentially. And they're all interconnected to one main network case, which is the main one that you see in the middle there. And so we use parallel simulation to basically have those all these various plants inside of their own essentially EMT cases, and then we can use electrical and data connections to talk back in between the cases. And if you do this right, there can you can do this with introducing very little inaccuracy to that interface if you do it very carefully. And you can have these simulations running in different time steps as well. So this is one way that we actually overcome time step issues and actually can overcome compiler incompatibilities as well if these cases are running in their own cases, dedicated cases. Other things you can do to increase the speed is to use average source models instead of switching models. Okay, so it's great. Some OEMs will give you models that you can just like flip a switch and switch between a switching model and an average source model. And if you have the average source model, you can run that at a higher time step, and therefore you can get a faster running simulation. We can use snapshots, but again, there is limitations here. Every model in the case has to be compatible with snapshots for you to use that feature. So it may or may not work for you. And you could use a larger time step. For example, inside of this, in this example on the right here, for that main network, we could use a big time step for our sort of system side case, and keep using the kind of recommended a time step that's within the recommended range for some of the smaller, for the individual IBR cases essentially. And then you could also, if it comes to it and you realize your system was initially too big and you want it to run faster, you make it smaller, right? It's kind of a last resort because you might be making some trade-offs between accuracy and speed at that point. All right, so a little bit about hardware, and this is very much from Electranix perspective. Other folks will have a lot of different opinions on this. But we in our shop, we like to use really high core count desktop machine. The server machines, we find they have, while they do have higher core counts, they seem like they're not really so much optimized for communication between cores, and also their sort of clock speed kind of per core lower a lot of the time. So we like to generally buy the highest core count AMD Threadripper that's that's commercially available. So right now our latest one is the 96 core, which can go up to 5.3 gigahertz, kind of at its fastest clock speed. And that's kind of, we would generally use this as kind of a shared machine between all kind of technical users in our shop. A note to people who are deciding budgets: these machines are expensive, and if you want to get serious about EMT and about doing big studies with lots of plants in it, then you have to allocate some budget for hardware, definitely. Few other points: liquid cooling is very important. Your chips are going to start clocking down the speed that they run at if they overheat. So you need to find a way to keep them cool when you're really pushing it to the limits. And lots of high quality RAM is also important, as the memory use is quite high for these cases. All right, you're up. Thanks.
All right, so what do you do with all of the output that we've been talking about from these machines, these big systems? What do you get? You get a lot of data output. And hopefully, if you've done it right and followed the best practices, it's neatly stacked, it's well organized, you know what it is, you know what inputs generated it, and you can then start to manage it if you have the right tools in place. And so, but it's an order of magnitude or two more data output than you would have seen from your PSCAD or your phaser domain types of tools. And it rises exponentially with the number of plants, because it's just not, there's more contingencies, there's more grid operating conditions with every plant that is added. And so it really blows up. And you can see why, one of the problems is certainly that we've been very sensitive to in discussing here is the scale, and how big do you go before it really just becomes intractable. And very keen to hear the perspective of some of the software vendors on that. But
really also it's one of the biggest bottlenecks in this is not actually in the vendor's control, but the models that are provided by the manufacturers is one of the big aspects of also of speed and runtime. But then, so then you have a lot of output channels, thousands of files, and it's just different from what we've been used to. And things that maybe you hadn't had to think about so much, like the sheer, like storage, for instance, of all of the data output now becomes a thing. And how do you sift through that output? All of the data the raw data is coming out as time series, as waveforms in time. And how do you go through that? It's impractical to have a person go through, or multiple people really go through and look at every waveform individually and assess, okay, this is good or this is a problem. You need a more systemic approach for that. And so what are the things also that you look for? There's no output plot that's going to, that comes with like the green light that says this is good or this is bad. And actually making that judgment, again, could be its own tutorial in terms of what is acceptable or not dynamically in these waveforms. Like even that seemingly, something like the acceptance criteria and judging acceptance, I think is easy to take for granted. And then when you get into it and look at all of the complex dynamics, especially at a system level that becomes a lot more nuanced and just not very clear. And so having an appreciation for that. There's a lot of things that are captured in EMT. Some of them are problem that will be exhibited in these waveforms. Which ones are problems, which ones are not? What was the original concern that was driving the study? And are you looking wide enough for problems that you didn't expect? It's easier to say, okay, we've got so much here, we need to be very focused and process this efficiently, but at the risk of missing something that you didn't expect that could be a real problem. So for instance, is this okay? Is this a problem? Are these cats or dogs, right? Sometimes you think it's easy and then you really get into it and you realize, okay, this isn't so straightforward. So what kinds of things can you see? You can see ride through failure. Okay, that's generally a pretty easy one to identify, right? But there's a lot of other things. And then momentary cessation gets into a gray area of, what is that exactly? And how much is it really stopping for? And voltage recovery and stability, right? And what periods of time, how low is the voltage? These dynamic swings as everything, especially coming out of a fault recovery. How deep does the belly of the dip go? How do you measure that? How do you account for that? That's going to be evolving depending on how much synchronous machinery versus IBR you have on a system. High extended and very high or extended transients. So the excursions, how much can you tolerate? Well, okay, this looks like an extreme value, but it only lasted for a very short period of time. We don't exactly have, we may not have a design practice written for what we've just observed here. So how do we make sense of whether that's a problem or not? High or low steady state voltages. Okay, undamped oscillations. I think those things are a little bit more familiar. Harmonic content, loss of synchronism or slipped poles. Usually those kinds of things jump out a little bit more. But the idea is there's a lot of different manifestations. It's not just, is your plant still online at the end of the simulation? It's a lot more nuanced than that. And judging whether it's acceptable per our planning and operations criteria or not, then becomes well, wait a second, we need to go back and think about this. And also that case, and also that case. And this is the part of the process where, okay, you've set up the model, you've collected all the data, you've validated the models, you've done all the run simulations, and you think you're on the home stretch. And then you get to this part of the stage and you start seeing these things and you're like, okay, well, is that right? Is that, okay, that looks weird. Is it right? well, let's go back and let's do a sensitivity analysis, and then let's chase down a rabbit hole in that model. And this is where the process also can go back and iterate. And that's actually quite common. And so it's one of those things, just when you think you're at the end and you're about to deliver your report, you start going through this and you get kicked back in some cases quite a ways. And if you're not anticipating that happening and you don't build that schedule, that can get uncomfortable if your expectations are not set accordingly. So other practical things, like what signals do you look at? We're talking about, I mean, easily many thousands of individual signals per case, which, I mean, and they're coming out in kind of the raw phase quantities. Do you have to look at RMS? Do you have to look at frequency domain? Do you have to look at and DQ? And there's a whole bunch of other aspects of that. So one approach for doing this is kind of taking it in layers and looking high level and saying, okay, you have some automated screening tools and processes, some techniques where you can have some automation basically look at all of the relevant waveforms for you and look for different markers of those. And just using that is, it's extremely important and powerful, but you have to be careful. You have to make sure that you're calibrated to look for those conditions and generally be set sensitive enough so that you don't miss any problems. That basically the automated portion is going to bring everything that could be a problem and then some things that probably aren't, attention of an engineer. And so, for instance, you could construct a heat map, if you will, of the cases and contingencies and all of the grid operating conditions and kind of quickly identify, all right, we're not going to spend very much time on the things that are green and clean. And we're going to zoom in, and just because it's red here, that's basically the signal to go in and look more closely and apply some engineering judgment and understand what's going on. Like this kind of approach can be really effective, but this type of stuff is often kind of developed custom for this type of stuff. A couple other reminders I would say, so on model fidelity, and we've tried to drive this home, right? Detail does not mean accuracy, and there's the false precision fallacy. And what comes out of these models, it looks like what you would have pulled off an oscilloscope or some, a DFR, right? It has all of this really cool, like really real looking waveforms coming out of it. Doesn't mean it's right at all, right? So, there's a 78.3712% chance y'all need another cup of coffee right now. That's, don't be fooled by that. I'd say, the steps that kind of guide my thinking here are, right, if what phenomena are occurring doesn't make sense, all right, what is the cause of those phenomena? What assumptions have we made, and you've always made some, that might be coming to bear on the cause of that phenomena? And are those assumptions still valid? Or should we go back and revisit those assumptions? And that's part of where the iterative nature of this comes from, is you may see something that looks funny, say, okay, let's look at that. What is the cause? We think it's this model or this aspect of it, but we didn't we used a Bergeron model instead of a frequency dependent model. Is that playing a role here? Okay, we think so. Do we care? Is it important? Well, yes, it could change the results of the study. All right, we've got to go back and change that line representation and rerun, well, maybe some subset or maybe the whole thing, right? And that's where you can really get kind of the game of ladders here, and you can kind of take a big shoot back. So answering those, I think, is important because, you need to have the confidence and be able to make the decisions and stand by them as a result of this, because obviously the stakes are very high. One aspect, so looking at the EMT model of validation, an example from ERCOT, And Julia touched on a little bit of this in the process, going from the generation interconnection. And maybe I'll go a little quickly here and save a little bit more time for Q&A at the end, because we got a lot of good questions about the process piece of this that we're going through. So for the generator interconnection, there's providing some models initially and having some basic model quality tests, and just understand that what you're getting is at least usable, that it's not a waste of time basically, or garbage, or just something plucked off the shelf and brought in as a means of box checking, right? We need to control for that. Going on to the next steps in the ERCOT case, specifically the QSA, more model quality testing, more benchmarking, and more detailed design phases thereafter, up to commissioning. And as we go through this process, you know, it's that diagram where we're showing the mechanical analogy of threading a nut on a bolt, right? And you start by hand and you have the big picture parts right. And as you get closer to commissioning and in the detailed design phases and in the subsequent iterations, that's when you really need to be getting to what the product is going to look like in the field. And then the operations aspect of it, being able to keep up on it, especially as things evolve, making sure there's that tie back to the models as well. A little bit on the mitigations that are available. So if you find problems, what do you do? What does it open up to? And so just broadly, you know, a number of the problems, I think starting at the left, they tend to be the lower costs, and then working to the right, the higher costs. And so usually you can kind of move from left to right. And there's each aspect of this may or may not be feasible or has different trade-offs. So for instance, inverter controls, custom engineering, those usually tend to be the lower cost options, but they are not no cost options. You get into a whack-a-mole problem sometimes on the control side, where you solve one problem and you break something else in another area. And I think that you can't overstate the reality of that. And that's what the manufacturers are so often very wary of, is they understand that, you know, we're kind of pushing the limits on all boundaries. And so to improve performance in one area can compromise it in another that's just as important. And so the inverter controls, they kind of seem free, but they're very much not so. The operations, and so for some folks, I'm sure, and for good reason, you know, remedial action schemes is a dirty word, but it has to be acknowledged that it can be cost effective from maybe a hardware standpoint, but it can be very much a massive problem on just the practical aspects of planning and operating a system that has, you know, that ends up in spaghetti logic. And I think it's important that be on the table, but, you know, there's a lot of folks where, and there's good reason for not having that as an option. Transformer design, so there's aspects of plant design that you can do to try to improve the behavior, or in a sense, some of the grid strength aspects of StatComs or SVCs, synchronous condensers, and really this actually, I made this slide before grid forming technology was has come into become such a presence. And then of course, there's transmission reinforcements, the kind of more traditional changes to the lines or addition of network reinforcements. Just to wrap up, and as we transition to the Q&A, you know, a lot of this is about achieving a balance and understanding what you're asking for, what the core question is, and making a lot of trade-offs here. There's nothing that's, you know, if there was anything, any no compromises thing, that they would have already been done, right? And so it really is the compromise. Are you going to be able to have as accurate a model as, you know, you're always going to find ways to make your model more accurate, but at some point that's just going to become at the cost of time, and it's going to, or budget. There's always going to be another contingency that you want to run, but you just might not be able to get to it. And so, and part of it in achieving this balance is I'd say there is a lot of pre-work that comes before you even start an EMT study, and understanding what are the conditions, what are the risks, and how are we going to, it's the scoping phase of it. And one other aspect that I want to mention briefly, this tutorial is not a power systems analysis tutorial. And so we are not covering all of the types of analysis. There is not just EMT tools and phaser domain tools. There are a lot more tools and approaches and techniques that we didn't talk about today that complement what we did talk about today. And so understanding how to use those other tools, from steady state even to identifying the contingencies that you care about, the grid operating conditions that you care about, to narrow the focus of these studies is really important. So on that, I know we're going to be transitioning to hearing from the major software vendors. Are we doing Q&A now?
No, I think we'll switch to a software vendor panel, and then we'll take Q&A for the last two sessions and for the vendors all at the same time, just in the interest of time, so we have enough time to give everyone the floor and speak up. So I would like to invite 4 vendors who graciously agreed to participate in the tutorial. So we have Jessie Lapsley from PSCAD, and Anton Stepanov from EMTP, Shijia Lee from Opal-RT Technologies, and Paul Forsyth from RTDS. So if you could all, come up here, have a seat, and we'll start with PSCAD. We will give about 12 minutes to each vendor to talk about the tool and what it's capable of, and then we'll have Q&A, and then we'll wrap up.
Space bar. Yeah, that's good. Okay. Well, good morning, everyone. My name is Jessie Lapsley, and I'm a system studies engineer from Manitoba Hydro International, MHI. So today I'm going to take about 10 minutes to talk to you about our software, PSCAD, and some of its available tools. So PSCAD has been developing and improving over the last about 40 years. To date, we have sold more than 46,000 licenses in over 100 countries, and we have an in-house support team of specialized engineers, developers, and IT experts to support our wide range of users. So, we'll hold it like this. PSCAD stands for Power Systems Computer Aided, and it's the user interface for our EMTDC simulation engine. So the DC simulation engine, it allows the duplication of any type of operation in a power system, and it covers all frequencies. It's only defined by a user-defined solution time step. So originally, like all EMT studies, PSCAD was used primarily for the historical technical stuff like SOV studies, TOV studies, simulation, coordination, all of this type of stuff. But as renewables started increasing their penetration, reducing the reliance on the synchronous machine, there became a need to investigate multiple frequencies within any type of simulation that we've seen, which in need of EMT simulations, as people have talked about already. So PSCAD was able to dive into other simulations that are large systems that we didn't usually look at, like any type of subsynchronous resonance studies, investigations of novel technology like grid forming batteries, and as well as dynamic wide area studies. So looking at the PSCAD graphical user interface, it starts with a blank canvas. If we start looking at the toolbar first, we have the Home tab where you can start and stop the simulation. The Project tab where you can set the simulation settings, like the solution time step you would like to use, how long you would like your simulation to run, as well as how often you would like your results plotted. Next, we have the View tab where you can control the canvas size as well as access the many panes of PSCAD. And lastly, we have the Components tab, which has some passive elements and some metering and plotting tools that you could use. They're very frequently used components in PSCAD. But our main modeling components are all categorized and organized in our master library. So, hello? Okay, so maybe I'll just hold it. Sorry about that. So here we have everything categorized as nicely as possible for our users. And we have extensive models of things like power electronics, transformers, synchronous machines, transmission lines, cables, and many more. So at this point, you would have everything you would need to attack those very technical and specific studies that were talked about as being historical EMT studies. This keeps on going off. But what about the wide area networks that we're starting to look at? For that, MHI has developed a tool called PRSIM, and it's our power systems importer. So what this does is it takes a large network database and does the necessary pre-processing to make a case usable in PSCAD. So currently, PRSIM can convert PSSE networks and power factory networks. With PSSE, we can import the raw data, the dynamic data, the sequence data, and the location data. The tool allows you to form network equivalents for unexpanded segments of the network, and you're able to reinitialize any type of new power flow you would like to investigate. So if you look at the graphical user interface for PRSIM, once you make a new case, you can import data. So in the case of PSSE, you can import raw, sequence, dynamic, and location data. And if you have your data in the Power Factory database, we also have an option for that. Once you want to start creating your network, if you do have a PSSE location file, you can use that. And if you load that, it will mirror the SLD that you created in PSSE. If you do not have that, you can simply right-click and add your first bus. So once your first bus is added, you can add multiple buses by clicking the plus sign within the box, and you can expand your network to whatever size you think is necessary for your studies. Once you're happy with that, you can export your network, and PRSIM will automatically create and calculate your equivalent sources to represent the networks beyond your boundary buses. Now, this would be able to be used in PSCAD, and you'd be able to start the validation process. And once validated, you'd be able to start adding your vendor models that you may have and running large system studies with that. Now, because you have potentially a very large network, this could slow down your simulation to very unacceptable speeds. This could also be the case for any type of resource-intensive component like an inverter. So for that, MHI has developed two forms of parallel processing that are very user-friendly. They are for different needs. The first one we call Electric Network Interface, or ENI. So this would be if you have two projects that run at the same solution time step that you would like to run together from different PSCAD projects. Our other option is called multi-rate. Now this is used if you have two projects that use different time steps, because sometimes vendors have specific time steps that you need to run their models at, and you would like to connect the two projects together. Both of these methods are interfaced using a transmission line, preferably an existing transmission line, so as you don't change your network in any meaningful way. So now you have all you need to run any type of large system study that you'd be looking at. To date, PSCAD has been successfully used around the world to run studies like dynamic fault analysis to integrate any type of renewable generation. We've looked at subsynchronous resonance studies, including any type of dynamic frequency scanning. It's been used to aid in the commissioning of new plants, as well as the investigation of novel technology, like grid-forming batteries, and comparing them to a similar size synchronous machine in performance. This is, of course, in addition to the historic EMT studies that we've already looked at. Now with this, you're going to have a lot of data that comes from PSCAD. And so what PSCAD, what MHI has also developed is a plotting tool that works in the offline environment that we call Enerplot. So there's a lot of features to Enerplot, and you can manipulate and track all of your data for any type of analysis. It does come with automatic scripting using Python as well as recording. It has embedded math functions, so you can manipulate your data as you see fit. You are able to template projects for any type of fast loading and repeatability. So for instance, if you have all of your data and you're going through a full impact assessment, you just have to set it up once, and then you would be able to just load in new data and it would repopulate all of your graphs for you. And it also loads your data quite fast. As was said earlier, a lot of this data comes not in the size of megabytes, but in gigabytes. So a typical project might need to load 4, 5, or 6 gigabytes per contingency that you'd be looking at. To make things easier for the user, there's also some notable features that PSCAD has, and I'd like to spend the last little bit of my time mentioning those. First is black boxing. So proprietary models developed by third parties can completely be black boxed in PSCAD. You can also black box controls as well as electrical models, in the process hiding all sensitive materials. This means that multiple vendors, each owning their own IP, can work together securely when using PSCAD. The next is automation. Now, someone had mentioned it in a question, and yes, PSCAD does have a very extensive Python automation library. This gives the user endless flexibility in how they want to run their PSCAD case and what they'd like to do with the resulting data. The automation library can be used to do things like run many simulations, change the model topology, export relevant information already to a report, automatically black box any open models, even send yourself an email to give simulation status on a simulation that you're running. Lastly is custom components. So you can make custom components in as much detail as you would like with PSCAD. This allows you to integrate any type of third-party models of any nature using these custom components. For example, complex controls are often developed in a C-based language and compiled as a DLL. This DLL would be able to be safely integrated into PSCAD, keeping all of its contents confidential. Finally, I'll just take a couple seconds to talk about our MHI support. So as I mentioned earlier, we do have a support desk staffed by highly qualified engineers, developers, and IT experts to help all of our users. It is available to any user, whether you purchase PSCAD or not. What we strive to do is ensure that your experience with our software is as best as it can be. If you have any problem, this is the best way we continue to improve our product, and we'd love to hear it. Well, thank you for your time.
Thanks. Thank you, Jessie. Next up is Anton Stepanov from EMTP. Go ahead, Anton. Just switch forward. There you go.
Right. Hello, everyone. So I'm going to start my presentation about EMTP. So you may be familiar with EMTP if you are in one of those areas, medical or maybe mail transfer protocol. But today we're going to focus on electromagnetic transients program. So there have been already a lot of information about the differences between phasor domain, transient stability type of software, and EMT type of software. So here's one typical example in how you may get difference in the results. In EMT, you get the instantaneous waveform. So you have, let's say, sinusoidal signals. In transient stability programs, you get the RMS values. And here is one of the practical examples of the results of the study you may get. So here we have a network with several wind parks, and we're simulating it into different software, some generic transient stability program without calling any names, and EMTP. So once the fault happens and then is cleared, we see that the transient stability program just shows you that everything is fine and the operation is back to normal. However, since it doesn't represent the control loop, such as inner current control or PLL, this result is not necessarily accurate and not realistic. And what you'll get in EMTP is that you'll see the instability because of these faster inner control loops. Now, EMTP is a software that allows you to do a lot of different types of simulations within one package. So you have the load flow, unbalanced three-phase, not only positive sequence load flow, steady state analysis. You can do time domain simulations, which is, let's say, often the most important focus of the software. You can do frequency scan, and all these types of studies are applicable in a variety of different areas. Large grids, we're going to take a look at some examples in this presentation. Renewable energy, IBR, grid forming, HVDC, basically any area you may think of, you can do it in EMTP, no problem. Now, the advantage of this approach that we have in EMTP is that once you assemble your network, you can do all types of studies. You don't need to import or export anything. Everything is done within the same package. So you assemble your grid in the user interface, provide the required parameters, and then typically you would start with clicking the button for load flow. So you find the load flow solution. And then based on these results, you do the steady state calculation of your network, you initialize your time domain system, you run the time domain simulation, and then get the results. All this is basically done with one click of the mouse once you assembled your network. There are, of course, many benefits. We can talk about that, let's say, later in the presentation. It's just a nice list of benefits of EMTP. We only have 8 minutes left. All right, so the basic package of EMTP consists of 3 items. First of all, the first thing that you see is going to be EMTP Works, which is the user interface. Then you have the computational engine, which actually does all the background work and gets you the nice results. And then you have the scope view, which is the program that allows you to visualize the data, plot the graphs, do analysis, compare waveforms, perform various comparisons and mathematical functions on the data. So let's start with the EMTP Works. This is the first thing that you'll see when you open EMTP. So this GUI allows you to perform to assemble your network in a hierarchical way. So basically you have different levels in your network. You can have areas and then go inside subcircuits to have more details in that area. It's very convenient and you have no restrictions, number of elements. It can handle very large grid easily. We're going to also take a look at a couple of examples today. You can automate many things because what you can do with the mouse, basically you can do with the scripting. It's fully automated. And we have many different APIs available. You can use JavaScript, Python, C#, MATLAB interfaces are available. So if you're familiar with these tools, you can program everything the way you want in the familiar environment. Now, here is the overview of EMTP window. You can have the there are different areas. Let's say you have the menu at the top where you have all the settings, the tabs with different subcircuits of your design or different designs. The main design area in the center, of course. At the bottom, you have the panel where you have all the information about the progress of your simulations or load flow calculations and all that. And on the right, you have the panel with the libraries where with a simple drag and drop, you can use all the elements that are existed in the library. Now, the scope view, the program that allows you to draw and visualize the waveforms, it is also possible to import data in a variety of different formats. So once you get to use scope view, you'll like it. That's our understanding, that you like it so much that you're going to use it for other formats of data because it will allow you to do many, many things. So you can do trigonometric functions, harmonic analysis, statistical analysis, and it's just an easy way to plot the data. So here you have a couple of sample windows. On the left, this is how the typical graphs would look in a simulation study. And on the right, you have another window which allows you to actually parameterize the things, perform the mentioned analysis. So you can do multiplications, FFT, and all that. All right, finally, the solver, which is, well, let's say the pinnacle of our technology. There are many innovations that we use in the solver that allows us to go to very large distances in simulation speed and accuracy of the results. The modified augmented nodal analysis and sparse matrix solver based on very special technique that allows you to do large amount of calculations in a short amount of time. The control system solver also very advanced. Well, there are many different things. So here's an example of what a matrix of your network may look like before and after what we call refactorization. So it's a technique that allows you to eventually accelerate the simulations quite significantly. Also, a couple of words about the features of EMTP solver that allows you to get results accurately. First of all, sometimes you may end up having numerical oscillations because of the integration methods you have. We have a solution for this in EMTP, which consists of using a specific integration method that just is not prone to numerical oscillations. So it's very good. For a couple of time steps, we would use this and then switch back to the integration method of choice, which you selected in the settings, which would typically be a combination of trapezoidal and backward Euler. Another very important aspect here when we deal with nonlinear networks, it is incredibly important to do iterations because you don't necessarily know if you change, let's say, slope of your piecewise linear characteristic of transformer saturation, where you're going to end up at the next time step. So you have to iterate to find the accurate point on this saturation characteristic. We do it with a full iterative Newton-based solver, and we basically have no restrictions of the size of the time step, even with the time steps as large as, I don't know, hundreds of microseconds. We can get accurate results when we iterate. However, if you don't iterate and just increase the time step, you can clearly see that the accuracy of the results is going to deteriorate. Finally, a couple of words about the control system solver. So it allows you to perform all the calculations of different types of control systems. You have transfer functions, discrete systems, integrators, gains, whatever you think of. And it allows you also to automatically initialize all the blocks depending on the, let's say, load flow results and what you feed in as the inputs or required outputs. So here's a couple of examples. Let's start with a simple one. This is a detailed Turkish grid with 4,000 electrical nodes with 3 different voltage levels and a lot of nonlinearities because you have detailed models of wind parks, you have a saturation of machines and transformers. The time step is very small, 10 microseconds. And once you assemble all this and run the simulation, you get 150 seconds, which is roughly 3 minutes for 1 second of simulation. So this is like the large network and you get the results in 3 minutes. It's very good. However, if you're not impressed with that, there is an even larger grid with 8,000 nodes, which, by the way, is a comment for one of the questions that was asked earlier. It was assembled by a Chilean company that had a couple of months, maybe 3-4 months experience with EMTP. All this network of 8,000 nodes and different voltage levels was assembled by them. And at the end of the day, with the parallelization of 8 CPUs on a regular commercially available laptop, you can get a simulation time of 30 seconds for 1 second of simulation time. It's not real time, but it's quite close to that. Now, there are many add-ons that you have here. We are listing some of them. Some of them that would be very, very useful for IBRs are renewables and maybe e-interconnect. We're going to take a look at them a bit later, right now. So the renewables library allows you to use the models for many different things that you need for IBR. So you can do the grid code requirement analysis, LVRT, OVRT, harmonic analysis. And to automate all that, we have a tool which is called e-interconnect, which allows you to perform all the tests required by a certain standard, let's say IEEE 2800 that has been mentioned here today quite often. And it will allow you to perform all the tests automatically, generate a report, which tests failed, which tests passed, what are the waveforms, the summary of all the tests. So all this is fully automated by this toolbox. We have another toolbox, let's say, for line cable modeling, which is based on so-called MOMSO technique, method of moments surface operator, which allows you to model basically any configuration you can think of, combination of lines, cables, all together separately, buried, over, underground, anything you think of. Okay, power electronics, facts, and HVDCs. So to model this accurately, you need to have good solver and advanced algorithms because you have a lot of switching. We have that in EMTP. You can get very good results and very fast initialization of all the systems. It doesn't matter how advanced they are. Right. Switching transients. Okay, I have basically 5 seconds, so I'm just going to mention it. Switching transients is also an area where you can use the EMTP a lot, and we have a lot of solutions for this. Protection analysis, protection toolbox, also going to be very useful. All right, then we have, of course, a lot of different references that are using the EMTP already. Right, thanks a lot for your attention, and hope you'll ask more questions when it's going to be time for questions.
Thank you, Anton. Thanks for keeping time as well. So the next 2 presentations we'll have from real-time simulators, and the first one is Shijia from Opal-RT Technologies. You just advance the slide.
Great. Hello, everyone. My name is Shijia. I'm with Opal-RT Technologies. I'm in charge of the power system team in the application department. So I'm very happy today to join my Canadian friends to be on this panel. Yes, it's very interesting that we're actually all based in Canada. I would like to introduce to you one of our EMT solution, which is called HYPERSIM, and how we can use it for interconnection studies and for large-scale system with high IBR penetration. So just a brief introduction on Opal-RT Technologies. We're based in Montreal in Canada, and we were founded in 1997. Right now, we have around 400 employees worldwide, and we have offices in the States, in Germany, France, China, and Brazil. So here in the States, we have an office in Denver, Colorado, where we actively collaborating with our customers, universities, and national labs. So about real-time simulation, I think I may need to take a bit of time to explain a bit like what is the real-time concept? How is it different from the other offline simulation tools? So the characteristics of a real-time simulation is the simulation speed is actually in real time, which means a 10-second simulation will take 10 seconds to complete. So you can connect your simulation with real hardware devices, for example, to perform some protection relay testing. So the device itself will think it is actually installed in the field. So you're injecting the voltage and current signals at the same speed as it is in real life. And the other advantage is that you're able to change the parameters or scenarios in real time while the simulation is running. So in that case, we're able to perform closed loop studies, which means the response of your controllers can be taken into account into the model to update the status of the model and to continue your test. So here we can have some examples of relay testing. We also support different communication protocols, which means you can do wide area monitoring and control applications using the synchrophasor data, for example. You could use IEC 62050 to test digital substation applications. And if you want to go one step further, which is to perform power hardware in the loop testing, that means you use an amplifier and then connect to a real converter, and then you may have a PV panel or a PV emulator, which is your actual system on the power level, and you can connect that to your simulation. So about our simulation solutions, we have actually a wide range of software. We support also electromechanical type of transient simulation, which is called EFASERSIM, that supports a larger scale system at a large time step. So basically that's RMS-based phasor domain solution. We also have EFPGA sim, which is a very fast EMT transient solution that you can use to simulate, for example, traveling wave protection application or very fast switching power electronic devices. So that is simulated on the FPGA at a time step which can be less than 1 microsecond. But what we're going to focus on today would be HYPERSIM. This is our typical EMT simulation, which would be running at 50 microsecond to 200 microsecond. The idea here for IBR integration, there are different type of studies we can do with it. So the first one would be software in the loop. It means that we run the model with the code of the controller. So it could be a black box model, or it could be a real code from the controller. And then we can go to hardware in the loop, which means you can connect to a real controller hardware. And as I mentioned, you could also interface power hardware in a PHIL fashion. And then if we scale it up, then you can imagine you could have a very large scale power system model with the integration of these renewable energies and this OEM controller code. And you can perform simulation very fast, and you can update the system conditions based on maybe your real operation data or from a state estimator. So you can update the operating condition of your model, and you can apply different contingency, different scenarios. So you can actually simulate multiple scenarios in a 5 to 10 minutes time frame. So here I have a video just to show a bit the workflow in HYPERSIM, and you see this is very similar to EMTP because in the like we're using a similar graphical engine in behind, and we all have our origins from the Hydro-Quebec Research Institute. So I'm just gonna play this video here. So this is the graphical interface, and on the top we have different menus. On the right we have the library components, and you can easily drag and drop a component and connect it to the network. So for example, here we could have control functions added, and then you can make the connections like that. And then I'll take a transformer as an example, and you can drag and drop it, make connections, and then you can open the mask and then change the different parameters of the component. You could also have subsystems. You can go inside, see the converter model, the PV panel model. I'm going to speed up a little bit. Okay, and here you can start the simulation. And here I select the simulator target. So this is a Linux-based target, which is optimized for real-time simulation. You can also do the same simulation on your PC on a Windows system. And when you're running the model, you can start scope view. It's the same scope view as the EMTP solution. And here you can do some live acquisition of the signals in the model. So here we'll be acquiring some power, irradiance, and voltage and current waveforms of this PV generation systems. And then you can do different type of analysis of the signals in the tool. And it has different mathematical functions that you can use to analyze the signals, to check the maximum, minimum RMS value, and also do harmonic analysis of the signals. So this would be the live data acquisition while the system is running. And other than that, we also have a data logger function that can be used to record signals from the beginning of the simulation to a specific time duration. It has trigger functions as well. So this can help you to do some post-analysis of the model. So a feature that I think is worth mentioning is in HYPERSIM, the model is decoupled automatically, which means for a transmission system, you may have a lot of transmission lines, which has a long propagation delay that would be longer than your simulation time step, let's say 50 microsecond. So in that case, the software will automatically decouple the model into different tasks and then to assign them to different cores of the simulator or your PC for parallel computation. So here it gives you an example. So it tries to estimate in each task how much computation time it will take, and then how many cores you want to run them on. Then it will automatically back different cores. So if we use this for IBR integration studies, I guess the workflow, as explained previously in this workshop, first, the thing you need to come up with your model. So either you build it from scratch or you import it from your existing tool. And then we can integrate some customized model, which may be site-specific or vendor-specific. And then we program a script to run different scenarios to do the studies that you want. So for the first step, in the last 5 years, we have developed a unified database that can be used to convert model from different softwares. So they can be phasor domain or they can be EMT domain as well. Here is just an example of an import from PSCAD, and then you could compare the results between these models. You could also compare the results to validate it against the real field recordings if you have it. And for this 118 bus model, in real time, it runs on 2 cores at 50 microsecond. And here, this is an example of import of a simple solar farm example that you also have seen this morning. So basically in the tool, you select the model that you want to import, and then it will gradually build the components and then make the connections, map the parameters. For EMT mapping, it's more straightforward, but if you're importing from a phasor domain model, then you may have some missing data because you do not have the same type of data in phasor domain and EMT. So in that case, we also do some assumptions. For example, for line parameters, we'll look at the voltage level and we will put the typical line impedance for that specific voltage level. And by doing that, we'll be able to have a reasonable propagation delay, and then that can be used to decouple the model. Okay, and about the OEM controllers, we're also able to adapt these pre-compiled black box models to work with HYPERSIM. Or if the OEM build a controller according to the IEEE or SIG guidelines, then it would be a lot easier to implement this code to make it run with HYPERSIM. So in this example is also a solar farm, and then we just make the outer controller into a black box, and then we import that to HYPERSIM, and here are just some results for different scenarios. So to be able to simulate different scenarios to have a very high test coverage, it is important to have test automation to help with that feature. So in this case, we have a Python API that can be used to change parameters, change operating conditions, and then generate test reports. And in the software itself, we also have a test view, which is embedded. So it's pre-packaged function, so you don't deal with the code, but you just put different steps together to form a test automation script. So just some other use cases. In the last 3-4 years, we worked closely with AMO to accelerate their simulation in EMT. So here we have a very large synthetic model, which has a similar size to the AMO NAM model. So it's around 4,000 three-phase buses, and it contains 150 IBRs. And then to come with it, it also have more than 300 pre-compiled DLL models. So for this one, we're running the electric circuit on around 80 cores to 100 cores on Windows Server, and then the controllers are executed in parallel on 300 cores. So to do this, we're able to achieve 3 times real time, which means that to run a 30-second simulation, it takes around 90 seconds. We also have some other use cases like Hydro-Quebec 1600 bus model. So this runs in real time at 40 microseconds on 56 cores. We also have examples with CPRI in China. They connect actually their HVDC control replicas to the model. This is also a very large model at 500 kV, and it runs at 50 microseconds on more than 300 cores. Recently, we're also developing the solution to do co-simulation between phasor domain and EMT domain. So in this case is a WAC 10,000 bus model. We imported a 500 bus model to EMT, and then to do the co-simulation with the remaining 9,000 bus in phasor. So it's still under development. Yeah, that's it. Thank you.
Thanks so much. And then last but not least, we have Forsyth from RTDS.
So I have
Morning, everyone. I'd like to thank ESIG for the opportunity to speak with all of you, and I hope you find this session interesting. I know that EMT modeling for many utilities is something fairly new, but something that we're all quickly having to come to grips with. So just to introduce our company and our product, RTDS Technologies has been in business for over 30 years now. We're based in Winnipeg, Canada, as my other colleagues. A lot of simulation technology seems to come from Canada. I guess it's the cold winters leaving us to do a lot of development in the dark. I don't know. Since those 30 years, our product is now in operation in over 50 countries around the world and over 500 installations. Our customers include leading electric utilities, electrical equipment manufacturers, particularly the vendors for HVDC, renewables and protection equipment, as well as research and learning institutions, so universities and national labs, and even consultants are now switching over to using real-time digital simulation for EMT modeling. Just to give you some idea of the global reach and the number of utilities that are using the system, we are all over the globe. We're still looking for a customer in Antarctica that will cover all continents, but haven't quite got there yet. In North America alone, we have approximately 30 utility customers that are using the simulator. So it is widely used, but still in many respects not so well known. Of course, this is the digital simulation technologies that we're talking about today. We cover many different areas of digital simulation. We need to be able to do load flows to be able to initialize the simulations. We can include RMS models as part of the simulation with a hybrid type model. But our focus is really on electromagnetic transient simulation. The simulation time steps will be in the order of 50 microseconds for a standard AC network, but we can also have the models running, or even portions of the model running with much smaller time steps to be able to incorporate the effects of fast switching converter models. So the RTDS simulator itself is a custom parallel processing computer. It's very modular in design. And of course, modularity allows us to customize the size of the system to whatever the needs of our customers are. And it is driven through a computer software, RSCAD, that's easy to use. So you don't have to be familiar with the ins and outs of the simulator hardware itself or the design. And of course, real-time simulation is primarily driven by the desire to test physical equipment. So we must have a lot of I/O available in the system to be able to interconnect with the outside world. At RTDS Technologies, we use a dedicated hardware design that is designed in-house by our engineers. The idea behind using the custom design is to have the ultimate in determinism and efficiency for the real-time simulation, enabling us to have very detailed models, very scalable models, and very reliable simulation technology. So this is a high-level view of what the system looks like. Every box is identical. They come with a 10-core processor, and the processor is connected to different FPGAs. The one FPGA controls all of the real-time communication to be able to connect to the different I/O, as well as to interconnect multiple modules, so to have that scalability. The other FPGA controls all of the non-real-time communication. So essentially, it connects to the PC and allows you to retrieve data from the simulation, the simulation results, to actually operate that model grid as it runs, and to be able to invoke faults and different operations in that network, change the operating point of the system, if you will. And essentially, you can act as the operator of that network that's being modeled. So in terms of the cores, the licenses can be added to the system to go from 1 core to 10 cores, depending on how much power you need for your model. And you can also add multiple chassis to the system. The RTDS simulator uses 2 levels of parallel processing. The first level of parallel processing is within a tightly coupled area. So you can use the different cores within a Nova Core chassis to model different aspects of that tightly coupled area. Or if you're modeling much larger networks, you can use multiple chassis and break up the network into what we refer to as subsystems. And you exploit the traveling wave characteristics of transmission lines and cables to be able to form those subsystems. And those techniques are used by all vendors of real-time systems to break up the system. And we've successfully built up networks with many thousands, actually tens of thousands of nodes within the system, and run those systems in complete real time. So the largest dimensioning of the system would be 144 Nova Core chassis. So with 1,440 cores operating together in your real-time simulation. All of these interconnected chassis share very precise timing so that they are operated in a coordinated way. So you have one large cohesive simulation. And you have ease of interconnection between all of these chassis. It's very important. You have a star point connection. So each one of them can communicate directly with the others. And this allows us to have these very large simulations. And of course, with the I/O modules, you can connect up many different replicas and have them interacting with those simulations. So the I/O can be conventional, analog, and digital I/O. Or of course, you can have Ethernet-based protocols, IEC 61850, C37118, DNP, etc., Modbus communication. And these protocols are then implemented so that you can communicate with the devices under test in exactly the same way as you would be connected to them in the field. We also have auxiliary hardware called the GT SOC, which combines an FPGA along with hard ARM cores that are embedded in the FPGA. And we use these models very sparingly. One of the main applications for the FPGA fabric would be to model MMC valves, multi-modular valves for HVDC or fax devices. But they can perform other functions. Probably the most important one today, especially with the discussions that we're having here about looking at inverter-based systems and their penetration into the grid, is to use this GT SOC box for vendor black box modeling. So vendors are creating black box models that operate and run on this actual platform, and that's connected into the RTDS simulator. So you have something that's very analogous to an external controller. The controller is implemented on the GT SOC, running on the ARM cores, and then that system is then connected into the real-time simulation that's running on the RTDS hardware. Our software is called RSCAD. The latest version is called RSCAD FX. It's a very comprehensive system. There are no add-in modules. Every package is exactly the same, so you don't have to add things to explore different areas of simulation or types of tests. And it's all developed at RTDS Technologies. It has a very rich component library that's been developed over the last 30 years. Been refined with interactions with our customers, including those international vendors that use it for their factory testing of their devices and systems. The components include power system components, controls, power electronics, HVDC and fax, protection, renewables. So everything that you would find in your grid is really available in the library. We also have a way of automating the operation of the system. using our scripting facility or through Python scripts. And our customers have used this capability for running hundreds or thousands of tests automatically without any intervention. And you can set these scripts up or the Python scripting up in such a way as it will create report-ready format results for you so that you don't have to have that interaction, manual interaction on every single case. The RTDS also has a multi-rate simulation platform. It's very important in real time to have better efficiency. So you don't have to use a very large simulator to model a small system if you have very high-speed power electronics. You can model a high-speed power electronics with a small time step and interface that system with a larger system model running at a larger time step. So the applications of the RTDS simulator are very varied, going from transmission level systems, standard AC networks for protection studies, also going into HVDC and FACS, testing of replica controls and tests at the vendors. We have distribution applications, so for microgrids or distribution automation testing, testing of protection, not only for 61850 digital substations, but also for conventional protection, looking at traveling wave-based protection. So the applications are very varied. I'll wrap up simply by saying that we believe that we're providing a very trusted platform with a company that has a very global reputation. We pride ourselves on our interactions with our customers and the support that we provide. And we're very engaged in being able to do custom developments or to add developments as the devices within the power system evolve. We need to keep pace, so we're very much trying to keep in contact with all of our customers to make sure we can provide the simulations that they require. Thank you.